We'll wait a little bit longer for people to join. Just a few minutes. There's a question. Or that might just have been a test to see whether I was paying attention. Okay, let's get slowly started. Maybe some more people will join, maybe not, but let's get started anyway. Okay, let me share my screen. All right, so let me start by showing you the website on which information about this particular training is listed. The likely most interesting part of that is in fact a link here to the GitHub repository. And the GitHub repository contains the presentation which I'm going to use, which is here. It's the, well, which is somewhere. It's the PowerPoint presentation. Yeah, this should be the one. So you can download that and well, have a look at it if you need. Other things which are of interest, of course, is the source code. And that is a number of directories in which per topic there is some example code to illustrate things which are mentioned in the presentation, which are mentioned in this training, and also a number of things for which there is no time, so you can consider that extra material. Yes, I'll put the link in the chat, no worries. What is also there for the more adventurous among you is hands-on, and that's basically a notebook which I am going to use to introduce Pandas features, and so you can either follow along in the complete notebook, or in this one in which you have to do some work yourself. Might be a little bit fast-paced for that, but anyway. So let me dump the URL in the chat. There you go. And let me also emphasize that if you have questions at any given time, please feel free to ask them. Probably, given the number of participants, it may be best to just ask them in the chat. I'll react to them either immediately because I keep an eye on the chat, or I postpone the reaction a little bit depending on what the question is and whether it's a good moment to deal with it, or better to leave it for a short while. But please feel free to ask questions. The more interactive this is, the more interesting it might be for you, and certainly the more pleasant it is for me, so feel free. Okay, let's start with the presentation, and then I'll switch to a Jupyter Notebook in order to show you some stuff. So basically, this is the QR code and the shortened URL to the same information which I posted the link to. So that is basically for face-to-face trainings, not so much here. This is our LinkedIn page of the VSC. So of course there's quite some information dissemination going on there on our activities on high performance computing in general. So feel free to follow us on LinkedIn. Okay, about the slides, some brief typographical conventions. Inline code fragments are typically rendered in this somewhat ugly monospaced font, just to emphasize that this is code and distinguish it from running text. Longer code fragments are in the same ugly font, but on a grayish background. And data files are on a yellowish background, or greenish, whatever this color might be. And one of the things which you notice is the triple dots, the ellipses, which is both in the code fragment and in the data fragment. That basically means that the screen real estate really doesn't allow me to put all the code or all the data there, but the code will have been explained on a previous slide or will be explained on the next slide, or you can just fill in the blanks because you know what's there. And for data files, it's just more of the same. Okay, so a little bit of motivation before we really get started. I would argue that Python is a very nice language for data science. It's really well suited for that, and there are a few reasons for that. One of the reasons is that it is a very terse language. I mean, with very few lines of code, you can actually do rather sophisticated things. And of course, the lower the number of lines of code you need to write, the faster your development cycle. That's one thing. And with some luck, also the lower number of bugs. Because if you look at metrics, then you will see that the number of bugs is actually proportional to the number of lines of code. So that helps. Also, it is an interpreted language, which means that you don't have an edit, compile, run cycle. You just have an edit, run cycle, and that helps a little bit in speeding up the whole process. It is a very good language for prototyping. So typically, if I have an idea for an algorithm, even if I don't intend to have the final implementation in Python, I still might create a prototype in Python to do some experiments to get some feeling whether the algorithm really does what it's supposed to do, to experiment with edge cases and corner cases, and just in general see whether the idea holds water or not. Okay. Also, very important factor in Python's popularity in the data science space is Jupyter Notebooks. The idea of notebooks actually has been around since the early 90s. People typically don't know, but the software system Mathematica had this idea of notebooks back in those days. But with Jupyter Notebooks and later on JupyterLab, this really gained a lot of speed, and people have even claimed that notebooks are key to doing reproducible science, which is utter nonsense. We can talk about that later, but they're definitely a great help in exploration, in data exploration, and in explorative programming. So they're very useful if used correctly. Okay, it's also very easy to access information in the sense that Python has a huge ecosystem, and that ecosystem contains many libraries suitable to read rather obscure data formats, to connect to databases, either the relational database strain or document stores, NoSQL databases, and so on. So it's very easy to get your information into your Python environment, into your Python script. And that's quite important as well in data science, since typically you spend quite a lot of time on data acquisition, data management, and so on. So basically for text-based information, you have regular expressions in Python, which are pretty powerful. And of course, you can read CSV files or other similar text formats, XML-based formats, and so on. You can also retrieve data directly from the web by scraping it. And then, of course, you need to interpret the HTML code. And this you can do with, for instance, Beautiful Soup, which we can talk about if there is interest on that. And of course, there is relational databases. And a very nice package for that is SQL Alchemy. Apart from allowing you to interact with databases, it is also an object relational mapping system. And that might be of interest as well. So that's another topic we can discuss. Also very important is, of course, the ease with which you can represent information. And given that we're talking data, very often data is in table-like structures, and that's where Pandas comes in. So Pandas has probably been one of the driving forces of Python in data science. Also, visualization is quite important, and there are many very nice libraries for doing explorative data analysis, like, for instance, Seaborn and HoloViews. Seaborn is a library that is particularly suited if you're interested in, say, more statistically oriented plots. We'll see a few examples during this training. There's also a dedicated notebook on Seaborn. And there's also HoloViews, which we will also discuss shortly, briefly. And that is a very nice library that with extremely little code allows you to do very nice plots. So that's important as well, that you have easy ways of visualizing information, visualizing data, scientific plotting, and so on. And of course, it is also, I'd say, the go-to language for machine learning with libraries such as Keras, TensorFlow, and PyTorch. And of course, scikit-learn, which is a very nice package. This is something we're not going to discuss during this training because there's a separate training, Python for machine learning, specifically discussing Keras and scikit-learn. So if you're interested in machine learning, there is a other training which is scheduled for this academic year, but I really don't remember when it's scheduled. You will find it on the VSC website. Okay, let's get started with pandas. I'll just use the introductory slide and then switch to a notebook to do things a little more interactively. So, what is pandas? Most of you are probably already familiar with pandas in the sense that you know that it exists and what it is, but let's discuss it nevertheless. So it's a library for data science. Well, it's a library to represent data, and of course, as libraries go, it contains data structures. And there are two important data structures in pandas. One is series, and that's to represent one-dimensional data, like for instance time series or other one-dimensional data. And then there is the data frame, and that's of course to represent two-dimensional data. There used to be a third data structure, which was a panel, and that was intended to represent three-dimensional data, but that has been deprecated. So I don't even know whether in the latest versions of Pandas it's still there, but it's going to vanish anyway. So even if it's still there, don't use it. Bad idea. It's going to go away. Apart from data structures, of course, you also need algorithms. And of course, if we're thinking data, then we're definitely also thinking data selection, and we're thinking data transformations. And one of the things which we will also discuss when we deal with the interactive notebook is pivot tables, which is a fairly powerful way of dealing with data. You might already be familiar with it from Excel, so it might not be new for you. Okay, then there's also a lot of utilities for visualization. For instance, there is a scatter matrix, which can be quite useful, and some other visualization methods. So essentially, Panda data frames are backed by NumPy, and that's of course a nice thing because NumPy is it's a very nice library, and it gives you quite some performance under the hood for Pandas operations. So that's a very good thing. Then it's nice to experiment with data, and of course it integrates quite well with Jupyter notebooks. So I would say that pandas are the R data frames for Python. So if you're familiar with R data frames, it is similar to the pandas data frames. Okay, so the convention is that you import pandas as PD. All right, so we are going to use an example dataset, and the example dataset comes in a Jupyter notebook. In an Excel spreadsheet. And the data is rather straightforward. We have 4 columns. The first column is a patient ID, and that's just a digit, well, a number, going from 1 to the number of patients. Now, at certain points in time, and that's represented by the date column, some measurements have been, well, a measurement has been made. The patient's temperature has been recorded. And also, the patient may have been administered a certain dose of some medication, of a drug. And as you can see from this spreadsheet, the patient's temperature is elevated. So basically, the drug is supposed to counteract fever, and the idea is, of course, to lower the temperature of the patient. Now, if there is a question, yeah, perhaps feel free to activate your microphone. That might be the easiest, or you can type it in the chat if you like. Meanwhile, I'll also put the URL to the slides and the repository again in the chat for those who arrived a little later. Okay, was there a question or not? Because I think someone raised a hand. No. Okay, let's continue. Okay, so that's our data set, 3 columns, nothing too exciting, 4 columns, nothing too exciting. Let's switch to some interactive stuff. Okay, perhaps a brief side note on how I'm typically working. So I always work in a Linux environment, in a shell, because that really speeds up things quite a lot. I'm not a big fan of graphical user interfaces in general, and I'm absolutely not a fan of Windows as an operating system for scientific work. You will notice that I'm in fact using a Windows environment, which is true because I really like PowerPoint. I'm quite a fan of quite a number of Windows applications, but not for science. For science, I use three things. Obviously, our VSE infrastructure, which is of course Linux. But on my own system, I typically use two things. One thing is just WSL, which is the Windows subsystem for Linux. This gives you a Linux implementation, a Linux distribution on your Windows machine. And in my opinion, this is a very nice way of working. It's also free, so that is quite convenient. Another way I'm typically working is using a virtual machine. And of course, you have a number of options. You can use VMware, which is what I'm using here. You can use the free player. This is the commercial version, the paid version, the workstation version, because I like some features which it gives, which you typically don't need, but okay. So that's another way I typically work, either a Linux virtual machine or with WSL. I'm going for WSL now because basically it's for free and it's easy to use. So basically I'm going that route. Okay, so another thing which is important in the context of data science is of course that you're able to reproduce your work. And that's typically where things like Conda come in. There are alternatives. There is Mamba, there is pipenv, there is Poetry, etc., etc., etc. So there are many ways to manage your environment. But personally, I started out doing this very early when essentially it was only Conda, and I'm still quite happy with Conda. It has the features which I want. So in the repository, I'm now in the directory, GitHub repository, you will see a number of things. One of them is an environment.yaml file, and the other is a specs file. And both of them allow you to recreate the environment, which I'm using for this particular training. So for instance, this is a YAML environment. As you can see, it loads quite a number of libraries which are required in order to run everything which is in this repository. Okay, so I'm going to activate my environment. All right, and now I have all the software available. I'm going to the source code directory and I'll start JupyterLab there. I use the --no browser option because I'm going to use a Windows browser in order to deal with my Linux running Jupyter kernel. So basically I'm mixing two operating systems here. And if I would not add the no browser option, then things would still work, but I would get some error messages from the Jupyter kernel because it tries to start a non-existing Linux browser. Okay, so I just get the URL, I control click on it, and I get the Jupyter Notebook. Now I would prefer to have that in a separate window. So let's, no, this is not what I want. Okay, that's better. All right. Okay, so I'm going to the pandas directory, and in the pandas directory, I want the, I think it's patient data. Or it's patient's IB. Let's see which one. I think it's this one, but I'm not entirely sure. Let's see. Yeah, that seems the right one. Okay. So you have this notebook. If you like, you can follow along, or you can just watch the screen, whatever you prefer. Let's try and get a little more screen real estate here. Work. Okay, I should be able to get this full screen without the menus, but I forgot which shortcut that is. Okay, what's going on? Okay. What? Carrot browsing. What the heck is that? No, this is not something I want. Okay. Can I expand here? Not really. Okay, whatever. Okay. What did I do now? This I also definitely don't want. All right. So let's get started. The first thing, of course, to do is to have a look at the data. Let's first see which things are required. So we import a number of things. Of course, the main thing is pandas, because that's what this notebook is about. But you also see that we're going to import matplotlib to do some plotting, numpy for some functions which we'll require later on, we'll see. Also Seaborn for some plotting, and we also use the matplotlib magic in order to ensure that the plots will appear in line in the notebook. Okay, once that's out of the way, and let me actually evaluate this. Otherwise, I don't have any. So basically, what do we want to do? The first thing we want to do, of course, is to get our data in. And this is an Excel spreadsheet. Now, Pandas is happily reading any Excel spreadsheet using the function read Excel. And the only thing we typically need to do is to just specify the file name. That's all. And the result is going to be a Pandas data frame. Okay. One of the first things I typically do when I get a data frame, while I import a data frame, is have a look what's in there. And the info method is very useful for that. And as you can see, it gives you a list of the columns in your pandas data frame. These are names. It will also list the number of non-nulls. So a null would indicate missing data. And as you can see, the numbers are not all equal. So there's 62 entries in the patient ID. There's 62 entries in the date, but there are only 61 entries in the dose and the temperature. So this already tells me that there is a problem with my data. I'll probably need to handle missing data, and we'll deal with that later on. What you will also see is the D type, so basically the data type of the respective columns. As you can see, patient is int 64, so that's an integer. Dose and temperature are double precision floating point numbers. Float 64 means 64 bits. That's 8 bytes. That's double precision. We'll discuss Pandas data types in a bit more detail later on. You also see that the date has in fact been automatically converted to a datetime time format. Also 64 bits, and as you can see, we have nanosecond precision, which might be a little overkill for our data, but okay, who cares? So that's quite interesting as an overview of what your data looks like. Another interesting metric not in this case, but in general, is the memory usage. And of course, this is a very small spreadsheet, so we really don't care about memory usage. But later on, we'll talk a little bit about how to keep your data manageable with respect to size. And that's an important topic. And then, of course, if you're dealing with larger data sets, keeping an eye on memory usage is definitely a good idea. Okay, so let's have a look at the data. And just to get a view, kind of an overview of it, it's always useful to use the head method. And that just prints the 5 first lines in your pandas data frame. And as you can see, it's rendered in the Jupyter Notebook in a rather nice way. It's pretty printed very conveniently. And as you can see, we indeed have the date time information. We have some numbers for dose and for temperature, and we have the patient ID. So let me perhaps emphasize that a lot of magic is going on here. So basically, the Pandas read Excel function is really doing a good job in automatically detecting the various data types. If that's not the case, read Excel and other read functions in the Pandas module have a lot of functionality in order to fine-tune that, to, for instance, specify the data types for the respective columns. So there's a lot of functionality there. Okay, so another function or another method which is really, really useful is describe. And this is going to give you some descriptive statistics about the columns. And for instance, here you see that we get, for all the numerical columns, we get this descriptive statistics. So we get the mean value, we get the standard deviation, we get the minimum, the maximum, and the various percentiles. So this is very convenient, especially the minimum and the maximum, because that will give you an idea about potential outliers. So for instance, if we look at the temperature, we see that the minimum temperature is 35.9. Okay, seems realistic. And the maximum temperature is 40.7. Again, realistic. If you would see a low number here, say, I don't know, 20 or whatever, as the minimum temperature, or you would see a maximum temperature of 50 degrees Celsius, yeah, then probably you need some data filtering, some data pre-processing, because that sounds at least unhealthy. So basically, that gives you some handle on what's going on in your data set. Of course, the average values, etc., of our patient column, well, that's pretty uninformative. Nobody cares. Of course, again, the count is useful, but we already had that information. Okay, so we seem to have 9 patients because basically the number of the last patient ID seems to be 9. Okay, but let's verify. So if we have a pandas data frame, we can actually get a series with a specific column just by adding dot and then the name of that column, patient in this case, and we can get all the unique values by using unique. Okay, and if we print that, you see that indeed we get 9 values and they range from 1 to 9. Okay, not particularly exciting, but using data frames in this way with the dot notation for columns is actually pretty neat. It works rather nicely. There is another way of selecting columns in a data frame, and that is by specifying a sequence of columns. So you might be a little bit surprised by the notation here. We have double square brackets, which seems kind of odd, but that is just because the square bracket operator is in fact overloaded, and it takes a sequence of column names. And that sequence is here represented as a list. Hence, the inner square brackets denote the list, the outer square brackets denote the operator. Okay, so out of our pandas data frame with 4 columns, we select the columns patient and date only. Okay, then we're going to group our data frame by patient, and we're going to count. So basically, this is going to give us the number of measurements per patient, because a date corresponds to a measurement. And if we group by patient, then we'll get a count of measurements per patient. Okay. As you can see, for most patients, there are 7 measurements, except for patient 6. Patient 6 only has 6 measurements. So maybe, probably, this is also some missing data. Okay, let's continue. Let's have a look at when the data, so the temperature and the dose, was recorded. And again, we use a method on pandas data frame, and this is a pretty powerful method. It's the query method. We'll encounter it a couple of times during this training. It's a really nice method. I typically use it quite a lot. Okay, so what are we going to query about? Well, the query takes a string as an argument, and that represents the query which we wanted to process. So in this particular case, we are looking for all the rows in our pandas data frame that have patient ID equal to 1. Okay, so query is going to produce a new data frame with only patient 1 data, but with 4 columns, with the date column, with the dose column, the temperature column, the patient column. Okay, but we're only interested in the date column. So again, we use the square bracket operator and the list, in this case, a list with a single element, which has the name of the column we're interested in this particular case, the date. Okay, so all the measurements have been taken on October 2, 2012. And the first one was taken at 10 o'clock, and then at 1 hour intervals, the last one at 4 o'clock in the afternoon, the measurements were taken. Okay, let's now have a look at patient 6, because remember, patient 6 had only 6 measurements rather than 7. So let's have a look. Okay, so again, the first measurement is at 10 o'clock, but the last one is at 3 o'clock in the afternoon. So basically, the last measurement for this particular patient at 4 o'clock is missing. Might be that the patient was released early or whatever, we don't know, but the data isn't there. Okay, so if you think about this data, then of course what you want to analyze, or the terms you want to think in, are those of a time series, because this is data which is time-based. At 10 o'clock, at 11 o'clock, etc., things were measured, the temperature, or medication was administered, that's the dose. So basically, we want to reason on this data as time series. Now, the current format is not particularly conducive to that, because the subsequent time steps are essentially in rows in this data frame. And yeah, I mean, how do I get data from one patient out, etc., etc.? This is really not convenient. And that's where data transformations come in, and specifically a pivot of our data. So that's what the pivot table method does. We start from experiment data, our data frame, and we're going to do a pivot. The new index is going to be the date. So a pandas data frame, I forgot to mention that, but an important thing of a pandas data frame is that each row has an index. And by default, that's just numbers between 0 and the number of rows in the data frame minus 1. So that's your default index, but you can have a different index. So what we're going to do here is we're going to create a data frame that has a date as an index. And the columns are going to be the patient. So if we do that, then you see that we get a new data frame. And indeed, the index in bold to the left is indeed the time. Well, daytime. Okay. And rather than having two columns with dose and temperature, we get dose and temperature per patient. So the patient data, which is the ID, is now the name of one of these columns. For the dose, those are the left 9 columns in our data frame, and the temperature, those are the right 9 columns in our data frame. And now, of course, the index is time. So each column represents a time series. And that's a much nicer way of looking at our data. Now we can analyze it much more easily. So one of the things which you might notice is that there are some nones here. See, here is a none. None means not a number. And that's Pandas' way of representing missing data. We'll deal with nones later on. There is one here for patient 4 at 2 o'clock. And there is another one here, the temperature, for patient 3 at 1 o'clock in the afternoon. So that's missing data. And then, of course, there's some more missing data for patient 6. We already knew that there wouldn't be any data for 4 o'clock. So in total, we have 4 missing values. We'll look at missing values more systematically in a minute. Okay, so it's very easy to visually represent a data frame, and we can just do that by using the plot method. We don't want to plot the entire data frame. What we do want to plot is the temperature. So again, we select the temperature column out of the time series data frame just by using the dot operator and the temperature. And to that series or data frame, we actually apply the plot method. And this is what we get. So we get a very nice plot without any work. So what do we get? The x-axis is labeled. And also note that the labels on the axis are in fact pretty intelligent, because the data was date time information. So we had the date and we had the time up to nanoseconds, displayed to seconds. But the plot method is intelligent enough to gather that the salient information here is just the hour. And we just get 10 o'clock, 11 o'clock, 12 o'clock, etc., etc. So I really like that because it really represents the information in such a way that we get the relevant information. We are not swamped with information, we get only what's relevant. So that's pretty neat. Another neat thing is that you get a legend automatically. So it's very easy to see which temperature, for which this patient, the temperature is plotted here. And one of the things we notice is that the green line, this one, is in fact interrupted. It consists of 2 parts, so basically that means there's a missing point here. We already knew that because we saw it in the table, but visually it's also immediately clear that something is going on here. So if we want to plot that particular patient in detail, very easy. Again, we have our time series, we get the temperature columns out of that, but we only want column 3. Oh well, column 3, that's not really what's happening here. But anyway, we want patient 3. Okay, So if we do that, you see that indeed we get the temperature for patient 3, and at 1 o'clock some data is missing. Now I set the third patient, the column. What is going on here? So this is a little bit weird, and there are people who would consider this a feature, and there are other people who rather dislike this. So the tree, you should not interpret the tree as the index of the column, because that is not the case. It is actually the name of the column, but that's a little weird. So if we go back to our pandas data frame, these things here, 1, 2, 3, etc., those are the names of these particular columns, but they are integers. Why? Because the original data was, of course, the patient ID column, and those were integers. So that's a little weird. Column names in pandas can be integers, and that's what's happening here. Hence, 1 would be the column for patient 1, not the column at index 1. That would be something different. Okay, so that's just something to realize, something to know, that column names can be integers, and that can be a little confusing. Because remember that Python is a zero-base offset language. So for instance, the first element in a list has index 0. So you might make mistakes if you don't realize that this is not a column index, but rather a column name. Okay, so let's have a more systematic look at where we have our missing values. Because of course, if you have a very small data frame as we have here, it's very easy to spot the nonce. If you have a data frame with 1 million rows and 50 columns, good luck spotting them visually. So then we need a more systematic way to find missing values. And there is a very nice method for that, which is called isNull. So isNull is going to create a new data frame with as many rows and as many columns as the original one, but with true and false as values. True if there is a missing value, false otherwise. Okay, again, of course, I'm not really interested in the entire data frame. What I want is a summary per timestamp. And this I'm doing using the aggregation method any. So any is extremely similar to the any function in Python, and it means if any value is true, then the whole thing evaluates to true. So nothing special there, similar thing to Python any. Okay, the more interesting thing though is the axis. You might know axis from NumPy. So Panda data frames also have axis. Axis 0 is column-wise. Axis 1 is row-wise. In this particular case, I'm interested in the timestamps, so the moments in time when there is missing data. So I want to aggregate over all the columns in my data frame. So basically, I want to go row-wise here. Okay, so I set axis to 1. And then you see that indeed I get a new data frame with as index, well, actually a series, which as index the timestamp, and as a result, whether or not there is missing data. So there is no missing data at 10 o'clock, 11, 12. There is missing data at 1, 2, and 4 o'clock in the afternoon. We already knew that, but this is a more systematic way of detecting it. There is also a nice additional package, which of course I completely forgot the name about, but if you look for missing data visualization in Google, you will easily find it. And that gives you a visual representation of missing data. So essentially, it will give you a very dense plot of all the rows and the columns in your data set, and missing values will be indicated in white. So that can be quite convenient in order to very quickly visually detect whether there is missing data or not. So if you're interested, have a look at it. Okay, so we actually want to have a look at the measurements at 1 o'clock and 2 o'clock in the afternoon. So in order to select a particular row based on its index, we can use the locator object. So again, note that the syntax is pretty weird here. We have our data frame, okay, no problem. And then we do .log. And if you're like me, you would expect that log is a method. But it's not. It's actually an object. How do you know? Well, basically because we are using square brackets here. You would really, well, I would really expect round brackets because, yeah, I expect this thing to be a method, and the arguments of a method go into round brackets, and that's it. Yeah, that would be it if log indeed were a method. Log is not a method. It is an object in your pandas data frame, and that object can be indexed using the index operator, so using the square brackets. And in the square bracket goes the index which we're interested in. So in this particular case, we get the dose and the temperature for 1 o'clock in the afternoon for all of the patients. And then we see that indeed the temperature is missing for patient 3. We already knew, but this is just to illustrate that there are different ways to get the same information. And of course, we can do the same thing for 2 o'clock. We notice that there is some missing dose for patient 4. Okay, we can of course make a plot of this, and that's what we get. Here is that missing point. Okay, so how do we deal with missing data? Well, the Pandas has a nice method which is called interpolate, and that helps us to deal with missing data. Okay, so just to experiment, we'll extract column the temperature for patient 3, the dose for patient 4, and we'll just do an interpolation on it. And we store the resulting series into two objects, interpolated 3 and interpolated 4. And then if you look at the result of the interpolated temperatures, you see this was the missing data point. So basically, we have a linear interpolation between the 2 points. Nothing special here. So that looks good. Similar for the dose. This was the missing data point at 2 o'clock. Now it's there. Okay. One of the things which is very particular to Pandas, especially if you compare it to NumPy, is that any operation you do in Pandas is going to result in a new data frame. Okay? For those of you who attended Scientific Python last week, if you have a NumPy array, then NumPy will go out of its way not to make a copy. The interpolation code, yes, here it is. So NumPy goes out of its way not to make copies of data. If, for instance, you slice a NumPy array, you will get a view on that same data, which can sometimes be quite confusing. if you're not aware of it. So the design reason for that particular choice in NumPy is that copies are expensive, and NumPy is there for performance. So if you can avoid copies, you want to avoid copies. Okay. So why the entirely opposite decision in pandas? Why does pandas always make copies? For performance, that's not really a good decision. So there must be another reason. Well, the reason is that no. So let me come back to that in a minute. I'll answer your question in a minute. It will be answered automatically. So pandas is always going to create a new data frame. So if I apply the interpolate method to this particular column, then a new series is created. The original data frame times series is not modified. Why is that? Because you use pandas very often in an exploratory setting. You're trying to get to grips with your data, so you do all kinds of data selections, data modifications, and so on. The problem is that if those modifications were in place and you make a mistake, you would have to redo quite a lot of your computations in order to get to the same point just before you made the mistake. And that's very inconvenient. It's also very error prone. So that's why, given pandas usage, it's a very nice decision that they decided to duplicate data. Now, just like you can force copies in NumPy, you can force in-place processing in pandas, and that's here. So basically, I'm happy with my interpolation, so I want to do it in the original data frame. So I'm going to do, on the time series, I'm going to apply the interpolate method. So it's going to interpolate all the missing data. That's the missing temperature for patient 3, that's the missing dose for patient 4, and that will also be the missing data for patient 6. But I specify the optional argument in place is true. So that means that the data frame is going to be modified and no new data frame is going to be created. So that's how to deal with that in pandas. And many pandas methods actually have this optional in place argument. Okay, so now the data frame has been modified. If we again do the is null and the any with access 1, you see that now everything is false. There is no missing data anymore. So let's have a look what happened for patient 6, because patient 6, remember, had some data missing at 4 o'clock in the afternoon. So the last data points were missing. And if we look at the temperature for patient 6, you see that the last temperature at the last recorded temperature, I should say, at 3 o'clock now is also the temperature for 4 o'clock, and the same for the dose. So basically, if your missing value is in the first row or in the last row, then the next or the previous row is used and duplicated. So that's how that works. Okay. So one of the things we might do just to let's do a help for interpolate. And as you can see, there are a number of optional arguments, and one of them is the method. So by default, it's linear, but as you can see, there are different methods which you can actually use. So there is nearest, and there are some piecewise. There are some other methods which you can use. For instance, you can even use cubic splines and so on in order to get your interpolation done more appropriately. Here I don't care, I'm just happy with the linear, but if you need more sophisticated ways of interpolation, as you can see, they are available. Okay, and of course you notice the in-place thing. All right, so as you can see, quite a sophisticated method. All right. So one of the things you might want to do is to get some extra data into your data frame. And what we want to do is we have the temperature information for each of our patients individually. But it might also be interesting to have the average temperature for all the patients. So basically, at each given point in time, the average temperature of those 9 patients. Okay, so if we want to add that to our data frame, then we need to add a new column. And that's really trivial. So basically, what we do is we have time series average temperature. That's going to be the name of our new column. And we compute that using existing data. So out of the time series data frame, we extract all the temperature columns. So those are 9 columns, remember, 1 for each patient. And then we apply the mean method, which of course is going to compute the average. And again, we specify axis is equal to 1. So basically, we do that row-wise. So we average over all the columns. Hence, we average over all the patients for each point in time. Okay. So now we can plot the average temperature. And as you can see, it goes up and then it goes down. And you see the time here from 10 o'clock to 4 o'clock in the afternoon. And the average temperature ranges between something a little bit below 37 degrees and up to a little below 39. Okay. We can also do something else, and that is for each patient. So the data which we have specifies the dose of the drug given at each point in time. But we might expect that it's not so much the dose at a given point in time, but rather the total dose which the patient got up to that point, which is more important. So we want an extra column for each patient now. And in that column, we want the cumulative sum for the dose. So basically, the first row will just contain the dose given at time point 1. The second will give the sum given at time point 2 and time point 1. The third one will give the sum at time point 3, 2, and 1, etc., etc. Okay, so for each patient, and of course we can get our patients by using time series dose, and then the columns there. So that would give us our column names 1, 2, 3 up to 9, and those are in patient. Okay, so for each patient, we compute the cumulative sum for the dose that that patient received. And then we create a new column, but notice this column index now has 2 strings. So cumulative dose is going to be the top level column, and then we have a second level column patient. And to that particular column, we assign the cumulative dose, which we just computed. Okay, if we visualize this, as you can see, we get something like this. And of course, it's quite reassuring that all the functions, all the lines here are monotonically increasing. If that were not the case, that would be very odd because it's a cumulative sum. It's supposed to increase monotonically. Okay, so of course, where we're working towards is checking an assumption or a hypothesis. So we might suspect that the temperature of the patient has something to do with the dose of the drug he receives. Okay, so we want to check an hypothesis. And to do that, we are going to use another pivot table. We start from our original experiment data, and again, we use the pivot table. But rather than viewing our data as a time series, we are now going to use the patient as an index. And we want two values. We want the dose and we want the temperature. But we also want to do some aggregation. So for the dose, we want the sun. And for the temperature, we want the maximum. So this is going to give us a data frame with two columns, dose and temperature, with a row for each patient, where the dose is the total amount of the medication that the patient got over the experiment period, and the temperature is the maximum temperature that that patient reached over the whole period of the experiment. Okay, and as you can see, this is what we get. And let's visualize that to see whether there might be a linear relationship. So again, we use plot, but now we want a scatter plot. So the plot object has a scatter method, and we specify the x-axis and the y-axis just by specifying the column name, and we also specify that we want a circle as a marker. And then you see that we get something like this, which with some imagination might indeed be a linear relationship. Okay, a very brief aside, I've also given this presentation to someone who was really into medical experiments. And that person told me that what I'm describing here is, well, not such a very good experimental method. Don't do this on real people because they might die. It's a very bad experimental design. Now, I'm not into experimental design for medical purposes, so I also don't know anything about it. So please consider this a tutorial on data analysis and not on how to experiment medical designs, because you will kill people if you follow my example. So don't do that. Okay, so there might or might not be a linear relationship here. Now, if we use Seaborn, then in fact we have a very nice plotting thing, which will give us some clue about that. So SNS, that's the typical way you import Seaborn. We had that import Seaborn as SNS, and it has quite a number of ways to plot data. One of them is an LM plot. And as you can guess from the name, it's a linear model plot. So it works quite nicely with Pandas data frame. The only thing which we need to do is the optional argument data we should set to the data frame which we're interested in. And the X and Y values are just column names in that data frame. Okay, so if we do that, then you see that this is what we get. And depending on the quality of your screen and the quality of the Blackboard collaborating, you should see a shaded blue region here, which basically gives you the confidence interval for this particular linear regression. So this is a rather nice way of very quickly visualizing your data, and I wouldn't say checking there is some linear relationship, but at least getting some indication whether it's worth looking into or not. Okay. So this was some data exploration. Let's go a little bit further. There is in fact another spreadsheet, and that spreadsheet contains metadata about our patients. And if we import it, I'm just going to import it immediately, you see that we have 3 columns and a number of rows. And the first column contains the patient ID. And of course, the patient ID in this particular spreadsheet corresponds to the patient ID in the other spreadsheet. So basically, we can join the data in those two data sets. Does it work with images? Depends on what you want to do. Of course, you can store anything in a column in a pandas data frame. So yes, you could have an image as a column, well, images as columns in a data frame. I've never tried this. So I've really no clue how pandas would handle that. But it's a very interesting question. But I can't answer you straight away. So yes, obviously, images can be in a pandas data frame. That's no problem. Whether something exciting happens with them, that's a totally different thing. For instance, if I were to show my data frame in a Jupyter notebook, I have no idea how that data would be presented. I don't think anything exciting is going to happen. It's probably going to be something like, okay, this is some object with some identifier and nothing more. But what do you specifically have in mind? Why would you want to do that? Okay, let's discuss that at some later point, perhaps. Okay, so other things in my spreadsheet are gender information and condition. Condition is something that can either be A or B, whatever it is. Gender is, I'm sorry, just male, female, no other things here. Okay, so let's explore the data a little bit. So one of the things which we might to know is how many distinct genders we have and how many conditions we have. Of course, it's very easy because this is a very small data frame. Again, imagine a data frame with a million rows, then you can't visually inspect, and you would have to do it systematically. So for gender and for condition, I'm going to extract that particular column and drop duplicates and get the values. Yeah, so basically to get some it would be possible, but not with pandas alone. If you wanted to do something like that, you would probably have to combine pandas to get the derived data, such as mean values or other parameters of the image. You would definitely 99.9999% sure need another library. And then I'd probably go for scikit image. And I'd use those in order to derive additional data, which then could be added as columns to your pandas data frame. So that would be entirely possible, but not in pandas alone. You would really need some quality quality image manipulation library, such as, for instance, scikit-learn or OpenCV. But a combination of those two would really give you what you want. Okay, so for our two columns, we drop the duplicates and we just get the values and we print them. And we also check how many we have. And then you see that indeed there is just two genders here and also just two conditions. Okay. Let's use the describe method again, because that was nice for our previous data frame. And now you will see that we actually get something a little different. So from the metadata data frame, I'm going to select the gender and the condition. and then I'm going to apply describe. And as you can see, I get something else, because remember what we got when we applied it to our experiment data frame. We actually got descriptive statistics. We got the mean value, the standard deviation, the quartiles, etc., etc. So that is very nice for numeric data. But this is not numeric data, this is categorical data. And hence the descriptive statistics which we get now is adapted to that particular data type. So rather than mean values and standard deviations as such, which are utterly meaningless for categorical data, we get the count, we get the number of unique values, we get the most common category, and we get the frequency of that. So basically, this tells us that there are more male participants in our study, 6 of them out of 10, and that there are more people with condition B, again, 6 out of 10. So again, this is quite useful. So let's have a look at query again. And now let's combine multiple criteria. So I'm interested in those patients out of the data frame, so those rows that have male patients, so gender is male, and condition is A. Note that I'm using the two types of quotes here in Python. I can use double quotes in a single quoted string without any problems. Okay. Also note that you need to use the ampersand operator to get a logical AND. For the logical OR, that would be the pipe operator. So that's a little annoying, but yeah, that's how it works. Okay, so these are my male patients with condition A. So query is quite powerful and you can get quite some sophisticated information out of it. Now, of course, the thing I want to do is I actually want to merge the two data frames, the one with the experimental data and the one with the patient data, to get to combine all that information. And this we can do by merging the data frame. Okay, so just to have a look at what we're going to merge on. Yeah, basically that's going to be our patient IDs, because that's the common identifier in both of our data frames. So what we need to know is, do all the identifiers in experiment data occur in metadata and vice versa? So in order to do that, we can use Python sets, and we just create a set out of the patient IDs in the experiment data and in the metadata. And that's, of course, patient's experiment and patient's metadata. And then we can compute the difference between those sets. So basically, patient 4 is in patient's experiment, but we don't have metadata for that patient. And we have metadata on patient 10 and 11, but those have not participated in the experiment. So we don't have metadata for 4, we don't have experimental data for 10 and 11. Now, of course, what we're actually interested in is the experimental data. So we want to merge our data frame, but in such a way that we don't merge in patient 10 and 11. Because we don't care, we don't have experimental data on them, so nobody cares. But what to do with patient 4? We don't have that many patients, so we actually do want to keep it. Okay, so we use the merge function in the pandas module, and what we feed it as arguments are the two data frames which we want to merge. Okay, we also have to specify on what column we want to merge. So that would be the patient ID, because that's the common identifier in both of these data frames. And the last thing which we need to specify is how we want to merge. And here we have 4 options. We can do a left merge, we can do a right merge, we can do a join, and we can do an outer join. Okay, what does that mean? Basically, it is how we deal with missing identifiers. So in this particular case, we do a left merge. And that means that all the patient identifiers of experiment data will be in the resulting data frame, even if that patient ID is not in metadata. On the other hand, identifiers that are in metadata but not in experiment data will not be part of our data frame. So that means we will get patient IDs from 1 to 9, 10 and 11, which are in metadata but not in experiment data, will not be part of our data set. So that's because we do a left merge. If we were to do a right merge, then we would of course use all the patient IDs in metadata, even if they don't occur in experiment data. And if there is an identifier in experiment data that is not in metadata, we would not use it. So basically that would give us rows for patients 1 to 3 and 5 to 11. Not for 4, because that's only in experiment data. And of course, we would have a lot of missing data for patients 10 and 11, because there's no experimental data for them. Okay. We could also do a join. That would basically mean that we use only those patient IDs which are common to both data frames. So if we were to do that, we would get patient ID 1 to 3 and 5 to 9. And then finally there's outer, and that would mean that we would use all the patient's IDs, both in experiment data and in metadata. So then we would use from 1 to 11. We would have missing data for patient 4, and we would have missing experiment data for patient 10 and 11. Which one to use depends on what you want to do. In this particular case, I'm interested in the experiment data, and I don't want to leave out any data which I have, so I'm opting for a left join in this particular case. And this is what we get. We get, again, patient dose temperature and date. We already had that. And we have additional columns, gender and condition. And of course, they repeat because for patient 1 is always going to be male and will always have condition 1. And the same for patient 9, always going to be male and always going to have condition B. So obviously this is a data frame with quite some redundancy, in the sense that this data is repeated for the relevant number of rows. Okay, no, not a problem, just something to realize. Okay, so that's our merge. It's very useful. So now, of course, one of the things which we have is that gender and condition are now encoded as strings. Let's perhaps have a look at this before we change things. So I'm going to insert something here. And what's that thing called? It's called data. Let's do info. And then you see that at the moment, gender and condition are object. And object is a data type that typically is used for strings. So gender and condition are string data, but yeah, I mean, they're categories. So yeah, it's okay, it works, but it would in fact be nicer if they were of a special type, which is called categorical. And we can make our columns categorical by changing their type. So I'm using the data gender column, and I'm using the S-type method, and the type I specify is category. So let's do that. And let's have a look at info again. So now you see that the type has changed from object originally to category for gender and condition. And that, in fact, is going to be a little nicer. One of the things which you might notice is that the memory usage went down. Of course, 3.4 kilobyte versus 2.8 kilobytes, I really couldn't care less. But for large data frames, and we'll deal with those later on, that is quite important. Okay, so if I do a describe, we already know this. So basically, we have 55 in total, and we have more males and more condition A, and we've got the frequencies here. Okay, so we might do some other queries. How many patients involved in our experiments are male and how many are female? Okay, so what do? We select out of data patient and gender columns. We don't want duplicates, and we do want to group by gender, and then we want to count. And then we see that we have 3 female patients and 5 male patients. Okay. Yeah, but wait, we had 9 patients. Yeah, indeed. But remember that for patient 4, we had no metadata. So the total number of patients we have metadata on is 8, 5 plus 3. Okay. So, other questions. Which patients had a temperature higher than 39 degrees and when? Okay. And we also want to display the gender. So again, out of data, we select the columns of interest. So that would be the patient ID, the date, because that's what we're asking for. When did it happen? We need the temperature and we need the gender. And then we just query for whenever all the rows where the temperature is more than 39 degrees. And if we do that, we see that we get 4 points in time where a male person had a temperature higher than 39 degrees, and 2 points in time where a female had such high temperature. Sorry, there are more of them. No, I forgot to scroll. So there are quite a number of them. I don't know how many, whatever. So actually, if you look at the data, then there are more male patients with higher fever than females. So let's count that. Again, we're going to do our query. We're going to select a patient and gender. Again, we're going to drop duplicates because we're only interested in the number of patients that had that fever, not in how many times they had it. So that's why we drop duplicates. And then we group by gender and we count again. And then you see that indeed, out of the 5 patients in total that had a temperature of more than 39 degrees, that in fact there's only 1 female and 4 males. So that raises the question, are there any differences in gender here? Of course, I prepared the data set, so yes, there are. But let's see. And again, let's look at the pivot table. So we want to see this again as a time series. Okay, so nothing new. We know how to do that. We have the pivot table, and we have as index, we have date, and as columns, we have gender and patient ID. Okay, and we already deal with missing data because we know it's there, so let's deal with it. All right, so note that now we actually have 3 levels of columns. At the top level, we have dose and temperature. For each dose and temperature, we have female and male. And for each gender, we have the patient ID. So these are our 3 patients, our 3 female patients, and that's the dose information. These are our 5 male patients, and that's the temperature information. So note that for columns, we specified multiple values. Gender, second level, patient, third level. In total, 3 levels of columns. Okay, so what we can do now is compute the male temperature, well, the temperature of the males average versus the temperature of the females average. So we have our gender series, that's the result of our pivot table. We get the top level column temperature, then we get all the columns for males, and we compute the mean value. Similar for females. Let's have a look at the type of this, and as you can see, that's in fact a series. Okay, so what can we do? Now we want actually a plot of the temperature, the average male temperature, the average female temperature, as a function of time. So we have two series, one for the males, one for the females, and we want to combine that into a single data frame that has the time as an index and two columns, one for males, one for females. Okay, so we can concatenate the two time series, and we do that along axis 1. So we put them next to one another, and that produces a data frame. That data frame would not have names for the columns. That would just be A and B, which is not particularly interesting. So we set the columns to male and female respectively. And then this is the resulting data frame. And of course, we can plot this. And then you see that indeed the average temperature for the males, blue line, is higher than the average temperature for the females, yellow line. Oh, isn't that great? Okay, so let's transform the data again. And in this particular case, again, we use a pivot. But now we're going to use as index gender and patient. So this is a multi-level index. We already had multi-level columns. You can also have multi-level indices. Okay. As values, we want temperature and dose. And again, we're using aggregation functions. So for the temperature, again, we want the maximum temperature. For the dose, we want the sum, the total amount of medication that has been administered. And we also set observed true. This is going to take care of missing values. Well, it's going to omit missing values, essentially. Okay, so now this is what we get. And as you can see, we have male, female, patient ID, and the dose and temperature for each of those patients. Total dose, maximum temperature. Okay, so as you can see, pivot tables are a pretty neat way of transforming your data into a format which makes it amendable for certain analysis. How do we export this data to high quality figures tables? Basically, it depends on what you're happy with. If you're happy with something like Seaborn, the output of something like Seaborn, then you're fine. Probably you're not. So basically, what I would do if I would really need high quality data, high quality plots, I'd just export the data as CSV, and I'd use my favorite plotting program in order to get high quality data. If it were for a LaTeX article, I'd probably go to, no, not directly to LaTeX. You would really have to take a few steps in between before you get to LaTeX. As far as I know, Pandas doesn't know about LaTeX. So you would have to go to some textual format for your data frame, probably CSV, import it into your favorite plotting program. For instance, if you go to LaTeX, that could be gnuplot, for instance, and then make your plots. There is not really a direct way to get very nice plots in Pandas. If you're not really, really very picky, you might use matplotlib. Then you can do LaTeX labels and some annotation. It looks reasonable. It's not really, really nice, but it's okay-ish. So if you're not too picky, you can use matplotlib directly on a pandas data frame. That's possible. But yeah, it depends on how nice you want it to look. Okay, so let's do a little more work on our data frame. Let me see. Yeah, let's do this and then have a break, because then we finish with this data frame. It's not that much anymore. Okay, let's have a little look at conditions. So we used the gender already. We didn't use the A and the B condition. So let's just explore a little bit. We have patient and condition. We drop all the duplicates, we group by condition, and we count. That gives us the number of patients that have condition A and condition B. And again, total is 8, because patient 4, nobody knows. We don't have data on that. Okay, so with respect to male and female, we can have a look if we take gender into account, and we group by condition and then gender. So we get a two-level grouping. And as you can see, there is one female with condition A, 3 males with condition A, and there's 2 and 2 respectively for condition B. Okay, so this shows you that you can do a group by on multiple levels. Okay, and again, we can visualize this using a bar plot. So basically, this is a bar plot for condition A female, condition A male, etc., etc. So again, very convenient. But yeah, you can't call this publication quality. This is for exploration, not for publication. Okay, so one of the things you might want to do is to go from numerical data to categorical data. That can often be enlightening. And for instance here, just by way of example, we're going to introduce categories for the temperature. We have 3 categories. We have normal, with fever, and high fever. So we use the cut method, which is in pandas data frame. We give it some values, which in this case is the temperature, and we also define the bins and the labels. So the bins should have one value more than the labels. So that means that everything between 35.5 and 37.5 will be normal. Everything between 37.5 and 39 is going to be fever, and everything between 39 and 43 is going to be high fever. That also means that if there were a temperature of, say, 35.4 degrees, it would not be part of this resulting data frame. Okay, so we're going to use the cut function in order to construct a new column in our data frame, which we're going to call status. Okay, and this is what it looks like. And indeed, we have a temperature of 38.3, and that's fever. We have 37.3, that's normal, and so on. Okay, so this is your typical way of going from numerical data, from quantitative data to categorical data, which can be useful at times. If you look at the information, you see that the status is automatically category. So it's not a string, it's category data. Okay, so we can describe this as usual. Most temperatures are normal, and that happens 27 times out of 61. And there are 3 unique values. Yeah, we know, I mean, it's normal, fever, and high fever, so nothing interesting. Okay, so now we can also query on this categorical data. For instance, we can select everything, every row that has high fever. Could you have it open? I don't think so. I think you'd have a very low or a very high value in order to get it open. But we can check the documentation if you want. but I think you'd have to do that by construction. Let's do the help. Maybe. This write looks interesting. And this red bins might also be interesting. So let's have a look at those. Okay. This is inclusion or not. So whether you're dealing with open or half open intervals. Then where was it? Red bins. Okay. No, that's not interesting. Include lowest. No, you would have to do that by construction. So basically, you would have to specify an artificial very low value if you want all the low values in the first bin, or a very high right value if you want all the high values in the last bin. You would have to do that by hand. I don't think there is an option for that. Not that I can see at first glance. Okay, so basically what we can do now is to query for high fever, and that would in fact be the exact same query, or result rather, which we already had by querying for temperatures higher than 39 degrees. So this should be identical. And then again, same query, status is high fever in this case, and we drop duplicates. So those would be the patients that would have high fever at some point. Okay. Are there any questions? If so, feel free to ask. I suggest we have a break now of, let's say, till 11:55. That gives you 12 minutes, ample time to get a coffee or whatever. If there are any questions, feel free to type them in the chat meanwhile. I'll also fetch some coffee, but I'll be back soon and check for questions and answer questions if there are any. Okay, that was bad. How do I wipe this thing? Okay, that's how to wipe it. And let's put the break till 55. Okay. I'll also put the URL again in the chat for those who joined later. Right. Okay. And I'm going to note the participants. Before I forget. Okay. Last ones. All right. And here's a question in the chat. Will I upload the recording? No. Well, yeah, yes and no. The problem is I can't make the recording publicly available because of GDPR. I mean, your names are here in the chat. Your names are in the participant list. This has been recorded. I cannot publish that without violating GDPR, because I never asked your permission to do that. On the other hand, I am making a recording, as you notice, so of course I'm keeping track of that. I do upload it to YouTube. It is unlisted, so it cannot be found unless I pass the URL to someone. So if you're interested in the recording, no problem. Just send me an email and I'll send you a link to the YouTube video. Okay. PDF of the slides. The LibreOffice again thing. Okay. Again, please send me email so that I know where to send it to, and also as a reminder. But I'll make the export immediately. What? Okay. Yeah. No. Here. Okay. All right. So that's done. And that was. But maybe I still have your email address. Yeah, I still have your email address. Here it is. Okay. Right, on the way. All right, I'm going for some tea. Otherwise, I'm not going to survive this. And then we can continue. Okay, so I've put on a poll because there are quite a number of topics which we can deal with, but not enough time to deal with them all. So there are a number of things. Let me just briefly explain what each of them is. So regular expressions are a way to deal with textual data to see whether a text matches some pattern which you suspect it will. Also, you can use it to extract textual data from a running text. You can use it to split data and so on. So it's quite useful if you're dealing with text. Relational databases, of course, I can't explain you everything about relational databases, but basically a little bit about how to interact with relational databases from within Python. So there are some slides on very simple interactions just using SQL, but also on object relational mapping using SQL Alchemy. So that's a second potential subject. And third subject is a little bit about dashboards. So basically how to present information for usage by potentially non-experts or by you to get summary information or something like that. So that's the third topic. And the fourth topic is graphical information systems. So how do you deal with geographic information? Can you query geographic information? Can you deal with data frames that also contain geographical information? And that's basically the idea. And that should be geographical information system, not graphical information system. Sorry about that. It also how to deal with satellite data. So basically with data that is either taken by a satellite or by a plane, something like that, aerial photography. So that's another thing which we can deal with. So if you have preferences, let me know. We should have time for at least two of these topics. Not for all of them, but two should be feasible. So those that get the most votes get dealt with. Okay. I think you can now see the number of votes. All right, I'm going to close the vote in 10, 9, 8, etc., etc., etc. And as usual, the winners are relational databases and geographic information systems. And I'm very surprised that dashboards is not popular at all. Okay. So let's close the votes and let's continue. I'll share my screen again. And I'm going to switch back to the slides for a second for a last remark on pandas. Well, a few remarks on pandas. So basically, what I wanted to talk about pandas or wanted to mention about pandas is that there are many ways to import data as a pandas data frame. So we've seen the read Excel function, but there is, for instance, also read HTML, and that would get a web page, and it would extract data that is in tables. So it will return a list of data frames, one for each table it encounters in that HTML file. That can just be a URL somewhere on the web. So that is that can be very, very convenient to get your textual to get your data from some website. Other data formats which are obviously supported are CSV, comma-separated value files. That is pretty obvious. There are also somewhat more obscure data formats which can be used. What you can also do is query a relational database, and the result of your query would be a pandas data frame. So that is a really nice way of interacting with data frames, so with interacting with relational databases. On the one hand, you have the power of SQL in order to query your database, and to more easily explore things, you can use pandas on those data frames. So that's quite convenient. Okay. Also, what pandas can deal with is HDF5 files, which can be convenient if you're into machine learning, for instance, or other fields where this is a common format. Okay. So one thing you can do is, I mentioned this in the introduction, you can have a scatter matrix. And that's actually a rather nice way to see whether there are, let's say, relationships in your data. So for instance, there are 4 columns here, 1, 2, and 3, and 4. And basically, this plot here plots column 1 versus column 2. And as you can see, there seems to be a linear relationship between those two columns. Of course, it's a symmetric thing. This is 1 versus 2, this is 2 versus 1. So basically, it's the same thing. On the diagonal, you get a histogram of this particular column. So this is a rather nice data format, and as you can see, it's very easy to get. You just need to use the scatter matrix function, which is in the plotting module of pandas. You specify the data frame and the size of the figure, whatever. So that's convenient. Okay, let me switch back to notebooks because there is something I want to talk about. Let me close this one. We don't need it anymore. But the one I want to show you is something. It should be something like data types. Pandas data types. Okay. All right. So I'm going to generate some data, and that data is going to be in a CSV file, just so that I can import it. So I'm using Padlib, which is in the standard library, and I'm using the random module, which is also there. Okay. So my data file is going to be random data to remove.csv, and there will be 100,000 lines in it. Okay. I open the file and I create a number of categories, some other data. Basically, here we have integers between 0 and 255, integers 0 and 1. There is some more data here, category data, which is taken, and there should be some real values as well, which are here. So basically, quite a lot of data. Okay, and let's import this as a data frame. And we're just using read CSV, so nothing special. And if we describe the data, this is what we get. So we get 2 columns of floating point values, and that's double precision. We also get a number of integers here, and as you can see, by default, they're int64. Now, int64 means that we use 64 bits or 8 bytes to represent our integer. That means that we can represent integers from minus 2 to the power 63 up to 2 to the power 63 minus 1. That's a huge range. Okay, and the same goes for the column which just had zeros and 1 in it. Okay, and our category here, that is just an object, so that's string. Okay, but this was category data, so basically something like 3 to 5 different values. I don't remember what I picked, but this is waste. So in total, this takes 6 megabytes. So of course I don't care. I mean, 6 megabytes, nobody cares. But multiply this by some factor, and of course then things get interesting. So let's see whether we can represent all this a little more compact. So one of the first questions is, do we really need double precision? Because if we don't need it, it's waste of storage space. That's one thing. But on the other hand, it also makes processing the data a bit slower. Because if everything is well implemented and we use the right libraries, etc., operations on single precision are faster than operations on double precision, if we do lots of them. So yeah, if we don't need double precision, then using single precision might be smarter. Okay, also our integers are way too large. So one of the things we can do is we can convert our float column to 32 bits, so single precision rather than double precision. And if we do that, you see that now the first column is single precision, and you also see that the size has gone down. It was 6.1 megabyte, now it's 5.7 megabyte. Okay, and of course we could do the same thing for the second floating point column. Okay, so that would help a little bit. Now, of course, we could do that immediately because I already mentioned that the read Excel file, but also the read CSV file, has quite a number of optional arguments. And one of them is the D type for the columns. So I want float 1 and float 2 to be a single precision floating point. So if I do that, and you see, if I ask the information, those are now single precision. Total size is 5.3 megabytes rather than 5.7. So in total, we saved almost a megabyte. So something like 12% of our data. No, that should be more. No, it's more than 12%. It's something like 16%. Okay, so that's good. What we can also do is noting that int1 and int2 were in fact values between 0 and 255. So that is a value which we can represent using 8 bits rather than 64 bits. So if for int1 and int2 we specify unsigned int8, that allows us to represent values between 0 and 255. And that's exactly what those columns contain. So if we import data again and ask for info, now we see that as type for int1 and int2, we have unsigned integer 8-bit. Okay, and the size went down to 4 megabytes. So we're coming from 6.1, we're now at 4 megabytes. So we've reduced the overall size of our data set, our data frame, by 1/3. Okay, and of course we can do the same thing for our binary column because that just contains 0 or 1, and the same for the category data. So we just specify that the type is category. All right. So now we go down to 1.3 megabytes. So this is a pretty huge reduction by a factor of 4. Almost. Well, no, a bit more than 4. So how efficient is it? We can have a look. So basically, if we have a single binary column, okay, what am I doing here? I'm just using column binary just to see how efficient this is. So basically, we have 100,000 binary values, and we need almost 100 kilobytes for it. So basically, that means that a single binary value is in fact represented by a byte. So we use 8 bits in order to represent a binary value. So yeah, it's not so very efficient, but it's okay. All right. Similar for categorical data. So if we look at the category thing, then you see that it also consumes a single byte per value. Okay. For integers, same thing. You see it's also 1 byte, 8 bits per integer. So nothing special here. Okay. So if you have data types and that doesn't correspond to the data, then there will be problems, but they're silent. So basically, this is an example. So we have a very large value here, which is fine as such. Oops, sorry, which is fine. If you look at the info, you see that we get a float 64, which is indeed what we would expect because this is a very large value here. This you can't represent in single precision, the 10 to the power 56, and also this value is too small to distinguish from 0 in single precision. But in double precision, it works. So we write that to a file, and we're going to import it. So just like we have a read CVS, we have two CVS. Okay, so now we can import the data type, and note that we specify float 32. Okay. We also have uint8 for b. Now, if you look at b, there is a problem since that contains -1. And it also contains 283, which is definitely more than 255. So this is not okay. So let's see what happens. And as you can see, we get 4 non-null values for each. So that as such is not a problem. If we look at the data, you see that we get a number of things which are somewhat unexpected. For instance, here, for B, we get 255. That should have been -1. But of course, due to overflow, this is going to be 255. Also, this one here, the 27, that would be the overflow for 283. So this fails silently. On the other hand, for the floating point data, the right thing happens in the sense that the very large value, which is too large to represent as float 32, that is just converted into infinite, which is fine. And the value which gives rise to underflow is going to be represented as 0. So that's fine as well. So be careful with data types. If you pick the wrong data type, you may silently get unexpected values. Okay. So that is good to know. Any questions about this? All right. What might also be of interest, but I'd suggest you just look at it yourself, is basically, where is it? Okay, now I can't find it. Don't remember which one I had in mind. The one about missing values. So basically, recent versions of Pandas have added quite a lot on how to deal with missing values. That was a big problem if your missing values were integer or string. Now that has been solved. So basically, there are new data types in Pandas which allow you to deal with missing data for integers, for strings, and so on. So that is very nice. It works pretty well. So that's something to explore if you're interested or plagued with missing values. Okay, let me switch back to the slides and proceed to talk a little bit about HoloViews. So HoloViews is one of the many plotting libraries for Python, and I really like it a lot from a design perspective. So it's very nice for exploratory data visualization, and I'll try to convince you in a minute. So it's very easy to create overlays. It's also very nice for parameter exploration since it has things like a grid space and a holomap. I'll show you what it is. And it interfaces nicely with NumPy and with Pandas. It's really nice to experiment with data, to explore data, and of course, especially in Jupyter Notebooks. The reason why I like it is that it's extremely simple to do complex things. So in general, when I write software myself, I try to make sure that very simple things are very, very simple, that simple things are very simple, that moderately complex things are simple, and that very complex things are doable. So that is typically my design goal, and that's also a design feature of this particular library. You will see it in a minute what I mean by that. So convention, import HoloViews as HV. Okay, let's do a trivial example. So let's plot some NumPy arrays. I create two NumPy arrays, one with x values, one with y values. You perhaps recognize the function from if you attended scientific Python. It's that attenuated cosine function again. Okay, so plotting it, we specify some cell magic output. We specify the size. Okay, and then we just did HV curve and a tuple with the x and y values. And this is what we get. And as you can see, it looks rather nice out of the box. Okay. That is quite forward. We can do more sophisticated things. So we create some more data and we combine plots. So we have a function f and a function g. The function f computes an attenuated cosine, the function g an attenuated sine function. And we create some x range, and then we create a curve, an f curve and a g curve. Okay, so again, just the HV curve thing, no problem. And we also set a label. And notice that we can use a LaTeX expression here. All right, so that was easy. And we are creating plots, we're not displaying them. All right, so if we want them side by side, that's very easy. We just add the two plots. I add the f curve to the g curve, and I get two plots side by side. And notice they are appropriately labeled with LaTeX typesetted labels. And we also get the x and the y axis labeled and so on. So that's rather neat. I mean, if you want to do that in Matplotlib, you'd have to create a figure, you'd have to do subplots, you would have to use axes, etc., and you would need 10 lines of code to get this done. With HoloViews, you just create two plots, you add them, you're done. Okay. If you want to have an overlay, very easy again. you just multiply the two curves. And as you can see, the result is rather nice. Colors are chosen automatically, blue for one, red for the other, and you also get a legend generated automatically. So again, quite convenient. Multiply two plots, done. I really like this design. It's really, really very nice. Okay, so I mentioned that you can use it with pandas, and that's true, but it's a little inconvenient since HoloViews doesn't immediately deal with pandas data frames. You need to create HoloView data frames, but that's easy. So we read our data, and this is gene expression data. Essentially, these are some genes. This is the expression level. These are agent, air pollution if memory serves, and those are quantities which were measured, and then the expression of the genes is measured. Okay. And I'm just going to plot that. I need to create a HoloView data frame, and then I can make a scatter plot out of that. And I'm just plotting the expression of two genes as function of one another. Okay, so this is a real life data set. At some point, I was interacting with some biologists, and they wanted an algorithm for something. Really don't remember what it was. They gave me a data set. I was exploring a little bit, and this is what I got. And of course, I asked them, okay, what's going on here? Because this looks weird. There is two groups in this data. You have these guys here, and you have these guys here. What's going on? Is this a real effect, or what's happening here? Yeah, they said, no, there is nothing going on here, because yeah, those are just householder genes. There should be no groups. There is no reason at all why there would be two separate groups in this measurement. Okay, I'm willing to believe them, but I don't believe them. So basically, what I decided to do was to do some clustering using scikit-learn, and basically this is what I got. So I got a blue batch and I got a red batch, and I told them, well, okay, I'm listening to what you say, but I don't believe you. I'm pretty convinced that there are two groups in this data. Figure it out. Okay. So they were sufficiently convinced that something was going on in order to have a look at their data set again, and they noticed something interesting. The interesting thing was essentially that the data set was composed of two batches processed at different points in time. So they had provided samples to a laboratory two times, one set of samples, second set of samples. First set of samples are the red guys, second set of samples are the blue guys. Okay. I made a different plot. So in this case, I have a distribution plot of the two batches, and I superimpose them using the multiplication operator with overlays. Okay. Notice, by the way, this is a distribution plot. I don't need to do anything. I get a histogram on the one hand. I could specify the number of bins if I wanted to, but I'm happy with this. And I also get a curve which describes the data. And as you can see, the red curve is a bit broader than the blue one. And so once that they realized that the red and the blue batches had been processed at different points in time, they also realized that that processing had been done by different lab technologies, by different lab technicians. And so basically, the person who did the blue batch had more experience than the one who did the red batch. And this is also clear from this plot, because there's much more variation. The standard deviation of the red curve is larger than the blue curve. So basically, this is just an illustration that with some data visualization, you can actually easily find problems in the data because, yeah, of course, this data set is somewhat unreliable due to this different processing. Okay, other things you can do, which are very useful, is using a grid space. So essentially, we are plotting the genes on the x-axis and the agents on the y-axis. And then for each gene, we get the plot for that particular. So we get the expression versus the agent concentration, which is on the y-axis. And again, this allows us to see whether there's a correlation or not. And there doesn't seem to be any correlation, which again is not unexpected, since these are Hauswalder genes, so you wouldn't expect anything here. Well, you might want to have a look at this one. This could be interesting, but okay. These definitely are not. Okay, but this is a grid space, and as you can see, that is very easy to make. We have the keys. Basically, that's just a list of of gene expression versus agent identifier, nothing more. And then you create a dictionary which contains plots, and these are just scatter plots, and you place them in a grid space by dimensions, gene and agent. Very easy. Okay. So another thing is a HoloMap. That's also rather nice. So basically, it's just an XY plot, nothing special, except that you have these pop-up things here. So you can actually specify the gene, and you can specify the agent by selecting them from the menu. So this is a very easy way to get an interactive plot in your Jupyter Notebook. Very nice for data exploration. Okay. We were going to skip regular expressions. Are there any questions about data visualization? Okay, if not, let's continue. And let's switch to relational database access. Okay. So basically, if you need a relational database which is in memory and which you can also save to disk, and which is very convenient and part of Python, then actually SQLite is a very nice option. If you need a real relational database, then you can use several databases. MySQL comes to mind. PostgreSQL is also rather nice. Oracle is a very good database, but of course is expensive. IBM DB2, again, commercial database. But MySQL and PostgreSQL are really nice. And of course, there is SQLite, which I already mentioned. So what do you use relational databases for? Basically to store structured data. Data that is easy to represent in tables. And the nice thing of relational database systems is, of course, that they are created to store large amounts of data and also to query that data very efficiently. So a lot of research has gone into query optimizers. So typically you get a very, very good performance. And you can access relational databases typically by command line clients. So MySQL, PostgreSQL, etc., etc. They all have dedicated command line clients, which you can use from a shell. There are also some more general purpose clients which you can use to access multiple types of databases. but in general, that's quite easy. And of course, there are many libraries for various programming languages to deal with queries to relational databases. There are also some GUI programs which allow you to deal with databases. And querying is using SQL, so structured query language, and that is a descriptive way of specifying your queries. Okay, so you try, of course, to use a database in Python using some standard interface. We do have a relational database coming with Python. It's in the standard library, and that's SQLite 3. And for simple applications, it's quite okay. Obviously, it doesn't have query optimization and so on. So if you need to do multiple joins, you're going to be unhappy with the performance. I once had a prototype with SQLite, and for production, I really had to rewrite my program in order to use another database because SQLite was just way too slow to deal with the entire data. It's fine for prototyping, it's fine for small databases, it's definitely not fine for large amounts of data. It doesn't work. Okay, well, it does work if you have patience enough. Okay, so if you want to access, let's say, databases like MySQL or PostgreSQL, you have dedicated libraries for that, for each of them, or you can also use SQL Alchemy, and that's rather nice because that also allows you to do object relational mappings, and I'll show you what that is. Okay, let's have a quick look at SQL. So basically, we can create a table, and the table is supposed to store data. So a table has columns and rows. The data is stored in rows. Each data item is stored in a single row. And you can view the columns as attributes of that data. So for instance, in this case, we create a new table if it doesn't exist. If it does exist, this does nothing. Okay, the name of the table is going to be weather. The table has 3 columns: city name, date, and temperature. And we also specify the type of the data. So city name and date are text, and temperature is real. Okay, so why is date text? Because SQLite doesn't have a date-time data type. Most relational databases do have this. MySQL, PostgreSQL, they would allow you to have a dedicated type for date-time information. SQLite doesn't have it. Bit of a bummer, but okay. Okay, so that's the type column. So real obviously means real numbers, so floating point values. Okay, we also specify not null here, and that means that if we insert something in our table, we must specify a city name, a date, and a temperature. We do not allow for missing values. If we try to insert missing values, we will get an error. So that's a nice thing about SQL tables. You can specify which information is really required, and you get an error if it's missing. Okay, so how do we get data into the database? That's with the insert statement. So we insert into the weather database. The columns we want to insert into are city name, date, and temperature. And the values are London 2012 something and 13.2 degrees Celsius. So the insert statement is intended to add a new value to your table. Querying is with the select statement. So we are going to select the city name column, the average temperature from weather, where the date is between two values. And we group by city name. So group by we already had in Pandas. So this is the same thing. We're going to group our data by city name, and we're going to select dates between in a certain interval. And for the temperatures during that interval for that city, we're going to compute the average value. So this is going to give us a table, well, output, with city name, average temperature for each city in our database. Okay. Modifying data is with the update statement. So we update the weather table and we set the city name to St. Petersburg, where the city name was Leningrad. So basically, if we had historical data where the name Leningrad was used for St. Petersburg, we just replace every occurrence of Leningrad by St. Petersburg if it's the city name. Okay, so that is SQL in a nutshell, except that we didn't talk about a lot of things, but okay. Things get interesting when you have multiple tables and then you start combining tables. Remember the merge function in Pandas? Okay, that would be the join in SQL, and the idea is exactly the same. Okay, so how do we do this from Python? Because this was just straight SQL. How do we do this from Python? Well, let's, for the sake of convenience, just use a SQL tree database. So the first thing to do is to create a connection. And that will connect to a file, which is WeatherDB, and that stores a representation of our database. Okay, once we have a connection, we can create a cursor. And the cursor is used in order to interact with our database. So we have our table created, but we want to insert data. So somehow data is generated with a number of cities, etc., etc. How we do this is not particularly relevant, but we have our data, and our data is a tuple of city name, date, and temperature values. So on the cursor, we execute a command, and that command is, of course, SQL. You recognize insert into weather, column names, city name, date, and temperature, and values, something weird. Question mark, question mark, question mark. Okay. Now, using Python, you would say, yeah, okay, why am I doing this? I mean, why the question mark, question mark, question mark thing? I could just put an F here to use an F string, and then I just put curly brackets, data 0, curly brackets, data 1, curly brackets, data 2. And I've got my statement, no? Yeah, true. Except that that is very dangerous. That would open up your application to what is called SQL injection attacks. So basically, if you don't really know where your data is coming from, your data, for instance, comes from a web application, then it might contain a crafted string such that the substitution of the last question mark, the last substitution of the string here results in another statement. That's very easy. I just have to put some value here, a closing round bracket, then a semicolon for my next statement, and then, for instance, drop table weather, which would remove the weather table from the database, which is not what I want to happen. So that's why SQL has this particular syntax, where you have the question mark thing, and the execute will substitute the values in the data tuple into the question mark positions, but in a controlled way, so that you're not vulnerable to a SQL injection attack. So this is really, really good practice Always use these placeholders. Okay, so the cursor is executed. That means execute this particular SQL command. Fine. Do that on all the data. Fine. But as you can see, this is a for loop. And when we have done all the inserts, then we do a commit. It's only from the point on where we do a commit that the data is actually in the database. So that means that if something goes wrong, we don't mess up our database because we didn't do a commit yet. So that's a big advantage. And when we're done, we just close the cursor. Okay, so that is going to populate our data. Now we can query it from Python. So again, we create a connection and we use a row factory, which is basically an easy way of iterating over our connection. We get a cursor again and we execute a query using our cursor. We have a select. It's the one which we saw before. So basically, we're going to compute the average temperature in a certain period. Notice question mark, they are here, start and end. And we're going to group by city name again. Okay, once we've executed our query, we can iterate over the results by just iterating by row. That's why we set the row factory here to SQLite.row. Okay, so row is going to be a dictionary, and the keys are the column names. So I'm going to print the city name and the temperature for each city. And when I'm done, I close the cursor again. All right, so basically, this is the way your typical library to interact with a database will work. So the example here is for SQLite, but there are similar libraries, not in the standard library, but available via pip or conda in order to interact with MySQL, with PostgreSQL, etc., etc. So very convenient. And the reasoning is always the same. You create a connection, you create a cursor, you execute, you iterate over the results, etc., etc. The way of working is the same. Syntax will not be a little different. Functions might be called a little different, but the idea is always the same. Okay, so SQL Alchemy, on the other hand, is a different kettle of fish because of object relational mapping. So, in a way, you can think of rows in a database in a table as objects in Python. So what an ORM lets you do is interact in your programming language with objects, but map that to rows in your table, in your relational database. That's basically the idea. So it goes in both directions. Let's have an example. So basically, from SQL Alchemy, we import lots of stuff. I'm not going into it now, but you recognize a few things like types and so on. So, okay. We also import declarative base. I'll tell you what that is later, and relationship. Okay. So the first thing we do is we create a base class. So declarative base is a function that is going to produce a class. Base is a class. And this we're going to use in order to define our objects. Okay, so we have a class, city. So objects of this class are going to represent cities. Okay, it inherits from base. All right. So we specify Dunder table name, and that's cities. So all the city objects which we're going to create in our application will be living in the cities table in our relational database. Okay. Then we have two columns, city ID and name, and those are going to be object attributes. They're columns in our database, and we specify the type of each. So city ID is an integer, and name is a string with at most 100 characters. Okay. There are some other things here. So for instance, the name of a string can never be null. Remember the definition, not null, when we created the table? This is similar. So a city always must have a name. The city name must also be unique. Whether that's a good idea or not, we can discuss about, because basically there is a St. Petersburg in Russia. There is also multiple St. Petersburgs in the United States, for instance. So is this good design? I don't think so, but we don't care. Basically, it's to show that you can specify that values in tables can be or should be unique. Okay. So that's for the name column. For the city ID column, there is also this primary key thing. And that basically means that the city ID is going to be assigned automatically. We don't have to do that. And they are going to be unique. And if we want to talk about a city in another table, we are going to use that primary key as a foreign key in that other table. So you can think a little bit of it. If I would give an example in real life, you could say that your what's it called in English? I don't know. In Dutch, your Rijksregister number. So basically, your okay, let's call it social security number. That would be the primary key, which identifies you in many tables in databases. So in this case, for cities, it's going their city ID. Okay. So essentially, we define a relationship between, on the one hand, a table in our relational database, the table cities, and a class on the other hand. And that's the city class here in our Python code. That means class is a table. An object of type city is going to be a row in that cities table in the database. Okay. So what else? We have a second table, measurement, and notice it also inherits from base. Table name is measurements. Table arguments is a unicity constraint. So time and city ID in this measurement table must be unique. I can have multiple rows with the same time. I can have multiple city IDs with the same value, but the combination of time and city ID in a row is unique. That's enforced by our unique constraint here. Okay. What's in our table? Well, we have a number of columns. We have a measurement ID. Again, it's integer and it's primary key. Okay. Then there is time. And as you can see, we have a datetime type here. Nullable is false, so we must specify a time. And there's temperature. That's floating point value. Again, we must specify it. Okay. Then we also have another column, city ID. That's an integer, and that's a foreign key. And the primary key it refers to is city ID in the cities table. So any value which goes into this city ID column must be somewhere in the cities table in the city ID column. So that's a one-to-one correspondence. And it's a foreign key because this key is a primary key in another table, in the cities table. Okay. And then we have something which is convenient. We can define a relationship. So city is in fact defined by a relationship to the city class. So that means if a measurement is made for a certain city ID, this measurement object will have an attribute city, and that will be of type class city. That's what the relationship thing does. So from my measurement object, I can directly refer to the city, and I can, for instance, get the name out of it without having to check the city's table myself. It's just an automatic relationship. Okay. And that's the ORM part of it, actually, the object relational model. All right, so we created our objects, well, our classes rather, and now we need to create our tables. So we need an engine, and the first thing we do is we create that engine. And here you see a string, and that in fact is some connector string to some database. So in this case, I'm connecting to a SQLite database. I could be connecting to a MySQL database, a PostgreSQL database, and so on. So this is going to be the connection string. For this, you need to check the documentation to see which is appropriate for your particular database. In this case, the only thing I need to specify is the name of the database, which is just a file name at the end of the day. Okay, then I've got my engine. All right. So if I want to create tables, I'm just setting metadata. So on the base class, we have metadata, and we just do create all using that engine. So this is going to create two tables in my relational database, if they don't exist yet. So basically the cities and the measurement tables. Okay, that's it. My database has been set up. I've got two tables. All right, so how do I get data into my database? Then we need a session. So again, this is a separate program, so we create a new engine, similar as before, and we bind the engine to the base class in the metadata, and we create a session. For this, we use the session maker, and we use the engine. Okay, once we have a session, again, this is a class, so now we can create a new session by instantiating this particular class into an object DB session. Okay, so this is something which is very Python-like in the sense that we have functions that create classes. And that's something neat that you can do in Python. There are other programming languages in which this is not possible, or at least not so easy. You can also do that in Java, for instance, but in other programming languages, this is not so straightforward. Okay, so let's create some objects. And let's populate the cities. So we use the city constructor. We specify the name. Okay, so we will get New York, Leningrad, and Paris. And for each of them, we make a city object. And then we add that object to the database session. So this is like the insert statement in SQL. It is going to insert a city each time we go through the loop, one for New York, one for Leningrad, and one for Paris. And the city ID, since it's the primary key, will be assigned automatically. Okay, so this is populating our cities table in our database. And as soon as we've done all the inserts, well, in this particular case, all the adds, then we can do a commit on our DB session, and the data will be really part of the cities table in our database. Okay, so we can use objects to express relationships. So basically, for all the cities in the list, we're going to measure the temperature somehow. So this measure temperature function does something given the city name or the city object. It's going to determine the temperature. Remote sensing, whatever, I don't care. That gives me a value. Okay. We also determine the date somehow, and that gives us a measurement. So now we create a new measurement, and we specify the time, we specify the temperature, and we also specify the city. And note, in our table, the measurement table, we do have measurement ID. That's automatic because it's a primary key. We have time, we have temperature, that's fine. And we had city ID. But here we are not bothering with the city ID. We are just specifying the city. And thanks to the fact that we had a relationship in our class, in our measurement class, the underlying SQL Alchemy engine knows that if I specify a city, what should I do? Well, I should check the city ID because that's the foreign key, and that's what I need to insert into the city ID column for this particular measurement. So that's how that works. And then again, we add the measurement and we do a commit at the end of the day. So this is very convenient. We don't need to worry about the fact that our foreign key is the city ID. We can just say, okay, this is a city, figure it out. So that's quite convenient. Okay, then we can do queries, and that's basically just method calls. We have the query method, which we execute on our session. And for instance, in this particular case, we are asking about the cities, and we want all of them. And that gives us the list with all the cities. Very easy. So basically, we specify the class which we want to query, and that, of course, underlying is the table in our database. So in this case, the cities table in the database. Very easy. Okay, a bit more interesting. Now we are going to do a natural join. So that's very similar to a merge with two data frames. Okay, so we have our DB session. We do a query, and we are querying measurement. Okay, but we join it to city. So basically, we want the two tables used. We are going to filter. The city name should be some name, Leningrad, for instance, whatever. The measurement time should be larger than some starting date and less than some ending date. Remember, in SQL, we could express that as where date or time is between two values. So this is the same thing, but of course, in this particular case, in syntax which is better, well, which is suitable for SQL Alchemy. And we want all the values again. Okay, so that's very easy to do. And this is a join on relationship. So basically, what we specify here is the relationship attribute which was in our measurement table definition or measurement class definition. Okay. So this is the select from where. This is the from part with the join, which we didn't see an example of. And this is the where part on city name and on the date of the measurement or the time of the measurement. Okay. So all of this works on class attributes. which is kind of neat. Okay, how do we change data? Well, if we modify attributes of an object, then our database gets updated. So let's select Leningrad. So we do a DB session query on the city table, and we filter for city name is Leningrad. And we know that there will be only one, so we just use .1 here. Okay. And then we change the name of that object, the name attribute of that object, to St. Petersburg. Okay. And we do a commit. Don't forget to do the commit, otherwise your object is changed, but the corresponding row in the city table in your database is not changed. So it's only when you do a DB session commit that that change is propagated. All right. So at the end of the day, the whole thing is just classes. So that means that, in fact, if I have a class that represents a table, that class can also have some methods. For instance, I might define additionally a dunder string method, which gives me a textual representation, a nice textual representation of my city object. So in this particular case, I have a format string here. So I would have city as a string, then a column, a space, the time in some format, and the temperature on another line indented by a tab. And then I format it with the corresponding values. Okay, so really convenient. All right. So one of the things, of course, is that if you use an object relational mapping, this hides the database interaction. So if you're not familiar with how relational databases work, you might write code that is very inefficient. So it's even if you think, well, okay, since I do use object-oriented mapping, I don't need to know SQL. Yeah, think again. Because under the hood, of course, everything you do with objects is translated into SQL statements, and some SQL statements are more performant than other SQL statements. In other words, some are extremely inefficient. So yeah, you still should know something about relational databases in order to use object relational mappings successfully. So that's important to realize. It's pretty easy to be inefficient. Also remember that, of course, object creation takes time. So if you have millions of objects around, you have created them. That will have created or taken millions of a small time, which may add up to a large time. So dealing with object creation and minimizing object creation is definitely a good idea. It can also consume really a lot of memory, because one of the reasons why you're interested in relational databases is that they do the memory management for you. All the data is in there. If you start instantiating lots and lots of objects, all that data suddenly is under the form of objects in the RAM of your computer. So now, I don't know, might be a problem. So basically, you really have to understand the relational model, and you also need some insight into how relational database management systems actually work. Okay, so this is a nice-ish introduction to how to design relational databases, because there's a lot of research that went into how to design relational databases properly. So this is something that you need to take into account to have a properly working database. All right. Any questions on relational databases, database interaction, and so on? Okay. Okay, this is slightly weird. But then what you are likely doing is using cut to get categorical data out of strings, because otherwise the whole regular expression thing doesn't make sense. Is that what you're doing? So you have, let's say, a column with textual data, and based on patterns in that text, you want to assign categories. Is that what you want to do? Because otherwise, I don't see where the regular expression thing comes in. The help I used. That is a feature. So the question mark thing, that's actually just a feature of Jupyter Notebooks. So let me just create one here, and I can ask help on anything I want. For instance, on the range function, Python's range function. I could also use alternatively, I could just use help range. That would do the same thing. But this is something which is specific to Jupyter Notebooks. You can also do the same thing if memory serves, because that's like an eternity ago that I did that. But let's try. So let me start new interpreter. So if I just start a Python interpreter, I think you can do the same thing here. Yeah, you can do the same thing. And probably question mark range is also going to work. No, it doesn't. So this you can't do. You really have to use the help function here. Get it. Okay. So what you're saying is if I do import RE and then I do something like range. No, range. No. I don't see the relationship. I don't see why it would work. But okay. Okay, this is weird. I really don't see the relationship. Anyway, any other questions on anything? Databases or pandas or whatever? If not, let's have another short break. This time a short one. Let's just say 5 minutes. Well, a little bit more than 5 minutes to make it a round number. Let's say 12:15, and then we'll deal with. Yeah, IPython is something different indeed. So that might, but I don't know whether I have IPython installed. I need to check because I've not used it for ages. Anyway, I'll have a look at IPython in a second. I'm just going to put the break thing in on the whiteboard. So that would be, oh, come on, 12, 15. All right. Okay, no problem. Let me see whether I do have IPython. I don't remember. Python? No, I don't have it. No. Yeah, okay, I can't test it now. As I mentioned, it's been ages since I used IPython last time. I typically just go to Jupyter Notebooks. I used to have it installed. Question is where? Maybe Python for scientific computing. That could be. Yeah, I do have IPython there. Okay. The question mark thing just does the same thing as in Jupyter Notebook. So if I just do question mark range, I get the whole thing for range. I think I can try with pandas cut. I guess I have that here. So import. Let's try the pd cut. Yeah, that also works. So normally in IPython, question mark something gives you the help, and you don't need to import regular expressions, whatever. So okay, I don't know what this is about, but for me it all works as expected without regular expression things. Ah, the source code. Ah, this I don't know. Okay, let's try that. Python. Okay. Import .pd. Okay. And then double pd cut. No, it just works. It gives me the source in the IPython without anything. Let me try it in a Jupyter Notebook. Okay. Double question or pd cut. Works. I get the signature, I get the source. It hardly does anything, by the way, since it just refers to some internal function, which then again is probably implemented in C or something like that. But anyway, for me it works. I don't need to import regular expression things. So don't know what's going on. Yeah, I did try IPython. I did try Jupyter Notebooks. Works both for me without issues. So I don't know where the import RE would come in. For me, I don't see reason, but okay. So also Scientific Python talks a little bit about visualization, mostly scientific visualization. So here we are talking mostly about, well, okay, mostly is a bit an overstatement. This is a bit more about data visualization in principle, although actually if I look back at what we've been talking about, it's mostly scientific visualization. But in the one about scientific Python, there is some stuff about visualization as well. I don't have anything specific on visualization because, yeah, it's a topic you can it's a topic that is pretty specific. I mean, certain visualization types are very useful in certain domains and completely and utterly useless in other domains. So that's what makes that a little bit difficult to give a general training about visualization. I also do have a training, well, I do have training material, and I sometimes give that training about visualization with ParaView. So basically, really scientific visualization of three-dimensional data and processing of data in ParaView. So that's another thing which I have training material about. But yeah, typically there are very few participants, so I only do that once every few years, basically. But it's a potential topic for training if there is sufficient interest. Apart from that, yeah, what I'm happy to do, if you would suggest, let's say, some specific topics, I could put together specific training on visualization, probably in combination with dashboards. That would be kind of interesting. And that's something that's definitely possible. But yeah, then I would need to know better, understand better what you require from the training, what you would like to take away from it. I would say contact me via email if you want to discuss this further. There are definitely possibilities. Okay. On dashboards, yeah. Yeah, dashboards are an interesting topic. We probably won't have time today. What I might do at some point is what I did before already. I also had a shorter training on notebooks in general, and especially tricks you can do with notebooks. And dashboarding is part of that. So I might do that one again and discuss nice applications of notebooks, dashboarding with notebooks, things like that. Okay, let's continue. I'm going to the slides, and I'm going to guess. Go to section. Graphical information system. Now I'm in doubt. Is this really graphical information system or is this geographic information system? I really have to look it up because I'm suspicious. I think it's actually geographic information systems. But anyway, training material on Plotly. Well, I do have training material on Streamlit. So I did some applications in Streamlit for data visualization. So yeah, there is training material on that, and you actually find it in the repository. Let me have a look. So I'm just going to show it here. So this is the repository, so same thing. So if you go to source code, you will actually see a directory called Dash. So yes, I have some material about dashboarding with Dash, not so much. I don't really like Dash, to be honest. There is also material on Panel. Panel is another dashboarding thing. And as you can see, there's also a directory on Streamlit. So there are some examples there. There are no slides or anything, but of course, Panel is pretty much self-explanatory since it's Jupyter Notebook. And Streamlit, yeah, that is just scripts, basically. But yeah, there is an example for that. Notice that if you want to use it, there is a specific environment here. I don't remember why. There was some incompatibility with the version of Streamlit and with my main Python for data science environment, and Streamlit horribly crashed and so on, so I had to create a custom environment for that. Anyway, so yeah, that I have. Plotly, not so much. So typically I use Bokeh for interactive plots. There is material on that, either in this repository, not really, but in the Scientific Python repository there's material on Bokeh. There's also material on Altair. Altair is also a very nice plotting library for interactive plots. And the nice thing is it translates to JavaScript. So basically, you can use it very easily in dashboarding applications. Altair is, well, not so easy to use. It's a nice library. You can do many things, but yeah, okay. It's a bit of a pain to use, but it can be worth it. So Plotly I'd turn to if I had streaming data, because that's one of the few libraries, or even the only one which I'm aware of, that allows you to deal with streaming data. Then I'd definitely go for Plotly. I did applications in Plotly a long time ago with streaming data. It was very nice until you needed your own server software in order to serve it. Then I decided to abandon it, but it's actually pretty nice. But I don't have examples here. I may have examples somewhere. Let me have a look. So do I have my training material repository here? Yeah, I do. And in the old Python directory, there is likely to be a Plotly example. Yes. So there's Plotly here. I'll put the URL of this thing in the chat. If I can figure out, yeah, here, and here, and then here, and repositories, and training material. Okay, yeah, that's not the right way to search for it, because of course everything is training. Yeah, that's better. Okay. So this is basically my old training material repository. Most of it has been migrated to various other repositories, but there's still some stuff in there which is nowhere else, so it's a bit, it's work in progress to move it. Okay. Geographical or graphical, I really need to check that. Information systems. All right. So, and there are a few systems out there, such as ArcGIS or QGIS. And the nice thing is, if you need specific things, you can program plugins in Python. So if you're really into GIS applications, then use one of these applications because it's going to make your life much more easy. I'm not familiar with these applications, so for me, I just use Python itself in order to do that. So one of the problems which you face if you're dealing with geographic information is that there are many file formats, many data formats. So there's shape files that describe shapes. There is GeoJSON, which is an interesting format that combines several types of information. So for instance, geographic information in the sense of shapes of a country or a city or whatever, combined with other information. And that's rather interesting. And there's also GeoTIFF, which is essentially for aerial photography for satellite data, things like that. Okay, so if you look at Python and GIS, there are some interesting I/O libraries that allow you to deal with these kind of data formats like Fiona and GDAL. There is a very nice visualization library which is called Folium. And for data processing and modeling, there is on the one hand Shapely and on the other hand GeoPandas. Okay, so for those of you who would consider following the Python for machine learning training. This is a data set I like a lot, and basically it's the World Happiness Index. It's just a CSV file, so nothing special, and there are a few relevant columns, which are the country and the happiness score. So basically it's score each country get, and the higher it is, the more happy the inhabitants of that particular country are. There is data for 157 countries, and we can just import it using pandas, using read CSV. Nothing special. Okay, so we have the country names, but we also need the country borders if we want to visualize them. So we have a GeoJSON file for that. Now we can create a world map using Folium. So we import Folium, we use Folium map. We specify the initial location of our map. So basically, we look at latitude 0, longitude 0. We choose a certain style, Mapbox Bright. These are the style of the tiles. And we pick an initial zoom level of 2, whatever. Okay. Then another thing is we now add choropleth, so basically our information, and this is the name, doesn't matter much. The data is the happiness data, that's the one which you just imported. The columns we are interested in are country and happiness score, and the geographic data comes from the GeoJSON file. Okay. Of course, we have on the one hand our pandas data frame, and on the other hand our GeoJSON file, and we need to have a common key so that the happiness score on the one hand can be linked to the outline of the country on the other hand. So we're going to join on properties name. Okay, then we have some fill color, blah, 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 opacity, and so on, line opacity, blah, 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 legend name, etc. Okay. So we're joining pandas and GeoJSON information, and this is what we get. So basically, this is a map very similar to Google Maps. So we can zoom in, zoom out interactively. We can pan around. There are different layers. Now there's only one, but you can have different layers. And as you can see, dark green countries are happy. Lighter colored countries are not so very happy. And then there is something that strikes you, which is that the United States seem to be particularly unhappy. Okay, they are about as happy as the Democratic Republic of Congo, so that seems a little bit odd. The reason is linkage problem. So the name of the countries in the two data sets should be the same and is not the same. In one of them, it's United States. In the other one, it's United States of America. So the key we are joining on, we are merging on, is unfortunately not entirely correct. So that is missing data. Okay, so in the World Happiness Index, we have United States. In the GeoJSON file, we have United States of America. So we need to correct one of them. So for instance, I can change the name in the pandas data frame. And if we do that, you see that suddenly the United States is also quite happy, which is good. And of course, you should do the same for all the country information which is missing. I'm guessing that Afghanistan is generally unhappy, which I can imagine, because this was data from 2015, I think. So they were unhappy then. They're probably even more unhappy now, but okay. So that's a way to generate maps very easily and to get your geographic information onto maps. And of course, depending on the zoom level which you use, you will get a more detailed or more coarse-grained map. And of course, you can zoom in and zoom out as you wish. So that's pretty great. If we want to deal with geometric objects, then Shapely is a very nice library, and it has, of course, a number of data structures, and one of them is a point. And the point can exist in either 2 or in 3 dimensions. So Shapely can be used in 2 or in 3 dimensions. We can combine points in a multipoint, and that's just a collection of points. We can have a line string, and that basically means a sequence of points, but it's ordered. So we have a first point, a second point, a third point. So a line string is not a a line string is a multipoint is not a line string. Then we have a multi-line string, so that is just more than one line string. So this would be your first line string, that would be the second line string. And they overlap, but they are not joined here. So they're 2 distinct line strings. There is a linear ring, so that's a closed line string, and it should never cross. So basically you cannot have a crossing there. And then finally there's a polygon, and that is a linear ring as an outer boundary, so that would be that square here. And optionally 1 or more, or 0 or more, linear rings as holes in that shape. So basically this guy here has 2 holes, these 2 rectangles. So the polygon itself is the green part, and it has holes which are indicated in white here. Okay. And if you have holes, they should not touch in more than one point. So they cannot share part of an edge. That's not possible. And then you have multi-polygon. So basically, this is one polygon, this is a second polygon, basically. Yeah. And those should not touch in more than one point, again, because otherwise it's just a single polygon. Okay, so some examples. This would be a line string. So we would have the points 0, 0, 1, 1, and 2, 0.5, and that would give us this particular line string. So note, these things here are actually screenshots from a Jupyter Notebook. So if you visualize a line in a Jupyter Notebook, a line string, then this is what you see. So that's a very nice way of dealing with geometrical data. In Shapely, you can immediately visualize it in Jupyter Notebooks. So I'm going to create 3 linear rings. This would be the outer one, and these would be the 2 inner ones. And notice, I don't have to, it will close automatically. So this is the first point, and the last point is going to be connected to the first point, because it's a linear ring. Okay, and I create a polygon out of it. So I specify the outer linear ring and the list of inner linear rings, and then that's what you get. Okay, so who cares? Well, the nice thing is that we can do predicates, so we can actually query things. So for instance, is A within B? Or does B contain A? That's equivalent from different point of view. Another query is, do they intersect? Do A and B intersect? Or in other words, are they not disjoint? Does A cross B? Is A almost equal to B? And then with a certain number of decimals. Is A valid? That's something which we need to check, because, for instance, we could create a linear ring which crosses, or we could create a multi-line string that's also invalid. So we have to take care that that's not the case, and we can always verify that an object is valid by using the isValid method, because you can create them. You can check whether something is a ring. You can also do spatial analysis, so intersection, for instance. Do they intersect? You can create a union. You can do the difference. You can do the symmetric difference, and so on. Basically, These are some identities which will hold. You can also get the boundary. So if I have a polygon, my boundary is going to be a line string or a multi-lines, a linear ring or a collection of linear rings. So you go one dimension less. So I can also take the boundary of a line, and that would give me 2 points, the 2 endpoints. You can compute the center it, so basically the center of mass, if you want, of a particular shape. And by the way, if you're unioning many objects, then you might want to use cascading union for performance. Otherwise, your performance is going to be very bad. Okay, so one of the things you can also do is add a buffer to an object. For instance, a point is 0-dimensional. If I add a buffer to it, it's going to be 2-dimensional. So basically, it's going to be, let's call it a small circle. And for line string, it's of course a 1-dimensional object. If I add a buffer, it will have an extent. So it will have a certain width. And that's of course nice if you want, for instance, a line string to model a street. A street is not a 1-dimensional thing. A street is a 2-dimensional thing. So if I add a buffer, I can make that 2-dimensional. And basically you see that here. So this would be the 2 line strings, which form a multi-line string. And I can add a buffer to that multi-line string with a given width. And then I can specify what these gaps should look like, whether that should be a straight angle or whatever. I have many options here. So this can be set with the join style and with the cap style. So this would be flat. This is a bit roundish. This is flattened. And the join style, as you can see, is miter here. So that's a sharp angle, while here it's rounded. And you have different ways of specifying the cap style. Well, you have different styles for the cap and for the join. Okay, so let's create an island. I like islands, I like sea. So basically, let's create our own island. So we create a coastline, and that's going to be a linear ring. And the island also has a lake, and that's again going to be a linear ring. So basically, what we should check, of course, is that the lake is within the coastline. If that's not the case, we have a problem. Okay, and then we create our island as a polygon with the coast as boundary and the lake as a whole. Okay, so this is our island. All right, then we create a number of cities, and a city is going to be a point. Okay, of course, a city should have a certain extent, so we're going to add a buffer, and we can make that buffer proportional to the population. The more people live in the city, the bigger it's going to be. Okay, and if the city is within the island, we keep it. If the city is not within the island, of course, we throw it away because cities can't float. So basically, if it's partially on the coast and partially in the water, we reject it. We don't want it. Similar for the lake. Okay, and then we create roads between the cities. But of course, those are line strings, very easy. But a road should be within the island. So we don't want a bridge over the lake. That's not something we're going to construct. Also, if a road would cross a bay, that's also not acceptable. And roads are simply straight lines, so nothing special. Okay, so this is our island with the roadwork and the cities and so on. So that's something that we can do, and you can do more interesting things. All right, so another operation which might be very useful is a convex hull. So basically, you have a shape and you create a polygon that forms a convex hull of those points. Also interesting is the envelope. So basically, that's the same thing, only you get a rectangle with sides parallel to the axis. So a convex hull tries to be as small as possible. The orientation is chosen accordingly. For an envelope, you just have the sides parallel to the axis. And you can do a minimum rotated rectangle and so on. So we have many ways to do that. Parallel offset. So basically, that is a line and then a line which is perpendicular. Which is parallel to it at a certain distance. So for instance here, we have a line and we have an offset of 0.5 to the left. So basically this is the new line. And then we again have to join level, etc., join style, etc. Okay. What you can also do is interpolate the distance from a point along a line. So we create 2 points, one at 1, 1 and one at 3, 3. We create a line that connects those points, and then we can create a third point, which is an interpolation of the line at a distance over 1. And that, of course, would be this particular point here. So the distance here should be 1. Then, if you compute it, you indeed see that the distance between point 1 and the new point is indeed 1. So that's quite convenient as well. Okay. Another thing which you can do is use GeoPandas, and that's a combination of pandas and geometric information. So basically shapefiles and GeoJSON. So reading GeoJSON is pretty straightforward. You can do that from GeoPandas just with read file, and then you can read a JSON file, and you can print the information. So in this particular case, GeoJSON file is country information, if memory serves, and basically what you get is 3 columns. One is the ID, the other is the name of the country, and the third is the geometry. So basically the shape of that particular country, the description of that particular country. Okay. Then what you typically want to pick is a coordinate reference system, and there are several of them. You just pick the one which is most convenient for you. Okay, then we can select things, and we have several selection objects. Remember, we had locate, so loc for pandas data frames. Here we have, for instance, CX. And what we have here is the longitude. So we go from 0 longitude to 10 longitude, and we go from 50 latitude to 55 latitude. And this more or less corresponds to Western Europe. So as you can see, we have selected Belgium, Germany, Denmark, France, and Great Britain, Luxembourg, and the Netherlands. Okay. And if we want to visualize this, it's very easy. Again, we can do a plot, and then we get this visualization. And as you can see, it spans those countries. Of course, note that the countries are selected in their entirety. So we were only selecting from latitude 50 to 55. But of course, France extends quite a number of latitudes downward, and we even have Corsica here. So basically, it selects the whole country, not part of the country. So that's something which you have to keep in mind. That's how it works. You can do shapely operations on GeoPandas, like buffer, like boundary, like rotate, etc., etc. So basically, GeoSeries and or data frames are transformed into GeoSeries. There is unary union, which basically will join a number of things into a polygon or a multi-polygon. There are overlay operations like union, intersection, difference, and so on, symmetric difference. And basically, this is like a join with like a merge with ordinary data frames. So basically here we have an overlay of Western Europe and Southern Europe, and we only wanted the intersection. We could do, for instance, a union. Then we would have all the countries in Western Europe and all the countries in Southern Europe. In this particular case, we just want the intersection. So that is just France in this particular case, because it's the only country which is common to those two data sets and which has overlap defined by an intersection. Okay, so again, we can merge data frames, just like we could do for pandas, and we're merging here on the name. So basically, we have a data frame, an ordinary pandas data frame. We rename one column, which is originally country, to name, and then we are going to merge information. We're going to, into the geodata frame, we're going to merge the pandas data frame so that we have extra columns. And in this particular case, from the merged data frame, we're going to plot the happiness score, and we are going to do that using an orange-red column map. So basically, again, dark red is happy, yellowish is not so very happy, and in this case, missing data is white. So obviously we have the same problem because our JSON file has United States of America, and our world happiness file has United States. So that's missing data. We should deal with it. But as you can see, it's a very easy way to get a quick visualization of your geographic information. Okay, there is also dissolve, and basically that means that you aggregate GIS information based on attributes. So in this particular case, we are going to extract some data. We have the name, the region, and the geometry. And what we want to do is the regions. So basically, countries are assigned to regions in that happiness file. So we have Western Europe, we have Southern Europe, I think, North America, and so on. And so basically, we're going to dissolve based on region. So that means we will actually only have one geometric object for an entire region, for instance, for Western Europe. And if you visualize that, then you see that indeed we get all the countries in Western Europe, Iceland here, Greenland most likely, the Scandinavian countries, Spain, Greece, etc., etc. Okay, so that's a nice operation which can be very useful to dissolve. Okay, so that's querying information. Another type of information which you may be facing is GeoTIFF. So GeoTIFF is in fact raster data. So basically it's pixels. At the end of the day, it's TIFF. So TIFF is a way of storing pixel data, and essentially it's just an array of RGB values typically. But that's not really, well, that's the case in ordinary TIFF files. But for GeoTIFF files, that's a little different. Because what you typically have if you have satellite data is that images are created in different bands. So in different raster bands. For instance, you might take an image in green, in red, and in blue, and you want those to be separate because, of course, for RGB, okay, this is a known format. We, as humans, we know how to deal with it because that's our visual spectrum, but it might be that our satellite also creates infrared. How are you going to combine infrared with visual information? So they need to be separate bands, and that's exactly what GeoTIFF is going to let you do. There's also some meta information. So very important is the coordinate reference system and also the geotransformation, because depending on the angle from which the data is taken, you will get some deformation. If you don't have sufficient information, you're not going to be able to transform your data or interpret your data correctly. So for I/O, GDAL is a very good library to deal with that, and there is a Python wrapper in order to deal with it. So we import GDAL, and we can open a particular GeoTIFF file. Okay, we can check the number of bands just by checking the raster count, the raster count of this particular file. And then each raster band itself is a NumPy array. So this would give me, now I'm not quite sure. I think that this is actually the first band and that it's one-based indexing here, as opposed to everything else in Python. I'm not quite sure anymore, but I think so. Yeah, it counts from one, indeed. I was right. And basically, this is what you get. So, of course, it's grayscale in the sense that each band is a single frequency. So it's just illumination, nothing more. So it's grayscale. Okay, so the projection you can get by data get projection, you get the geotransform similarly. If you want to create your own GeoTIFF file, then the first thing to do is to get a driver, which you get from the GDAL library, and then you create new data. So you specify a file name, and you specify the raster size, and the number of band, and also the encoding. So this is geodata type byte, so this is a particular data type. Okay, and yeah, it depends on what you want to encode. So in this particular case, you would have 1 byte for each pixel. You can also choose to have a single position floating point number for each pixel. So there are many options here. It depends on what you need, what you pick here. And then you have to set the projection and also the geotransform. And then you just write NumPy array to that particular band. And you flush the cache. Once you've done that, you have a GeoTIFF file with meta information. So how do we deal with geotransformation? Because we need to know. This is actually a mapping from a pixel to coordinates. And these are the transformations which you need to apply. So basically, what you need to specify is this GT0, GT1 up to GT5. And they, of course, define a linear relationship between the X and Y pixel and the X and Y geometric coordinates. So this is something which you need to get right. So G0 and G3 are the top left corner of the left pixel. And then GT2 and GT4, if those are equal to 0, it means that the image is north upward. And GT1 is the pixel width, and GT5 is the pixel height. So these are things which you need. So here you see the 2, so that's the, here you see the 1, this is the width. Here you see the 5, that's the height, etc., etc. So this is the formula in order to get the geotransform right. Okay. So some further reading. There's a Folio manual, Shapley manual, GeoPandas manual, and so on. There is a nice introduction to geographical information systems and Python. There is a manual on Fiona if you need that. That's the I/O library, and something about editing and displaying GeoJSON data sources, which is rather nice because if you can. If you have some data sources available, it's always nice. If you need some visualization, you can easily find some input files, for instance, the shape of countries or something like that, or satellite imaging of a certain country to overlay on your plots and so on. Okay. So, any questions? All right, if not, I suggest we conclude here. Feel free to ask any questions now. If not, thanks for your participation, and perhaps I'll see you for some other training event in the future. Well, the problem is with respect to the geotransformations, not that well, in the sense that it is linear. The whole thing is linear. So basically, you get the curvature correct if the area covered is not too large. If it's very large, I'm afraid you will get problems. But for normal data, it should be okay. If you would try this on an image, a very large, well, an image that really spans half the globe, yeah, that would not work. But for aerial photography, no problem. For satellite images, as long as you cover a reasonable area, no problem either. Yeah. Yeah, on condition that the area covered is not too large. Otherwise, you would have to do something a bit more intelligent than linear. So I'm not so sure that GeoTIFF is the best format for that kind of images. I would say everything Earth related fine, but the sun is really, really large. And depending on how you make your images, whether an image spans the entire surface, for instance, then no, you would need a different transformation. My pleasure.